Newton's laws of motion. When we watch a ball roll across a field, or a car speed along a highway, we are witnessing the fundamental rules that govern how objects move. Motion is all around us, and understanding why things move the way they do helps us make sense of the world. The study of motion is not just about curiosity. It affects everything from designing safer vehicles to launching satellites into space. Knowing the principles behind motion allows us to predict, control, and innovate with the forces at play. Newton's laws of motion are a set of three principles that describe the relationship between an object and the forces acting upon it. They form the foundation of classical mechanics, explaining why objects start, stop, or change direction. The first law, often called the law of inertia, states that an object will continue in its state of rest or uniform motion unless acted upon by a force. The second law defines how force, mass, and acceleration are related, often expressed as force equals mass times acceleration. The third law explains that every action has an equal and opposite reaction. These laws involve key components such as mass, which measures the amount of matter in an object, force, which is any influence that causes a change in motion, and acceleration, which is the rate at which an object changes its velocity. Together, these elements describe the motion of every object we observe. The story of these laws begins in the 17th century, during a time when scientists sought to understand the natural world through observation and experiment. Although ideas about motion existed long before, it was Isaac Newton who formulated them in a systematic way. Newton built upon the work of earlier thinkers like Galileo Galilei, who studied falling bodies, and Johannes Kepler, who described planetary motion. Newton's laws were published in his landmark book Philosophiae Naturalis Principia Mathematica in 1687, marking a milestone in science that changed the way people understood motion and forces. To understand how these laws work, consider a simple example. Imagine pushing a stationary bicycle. At first, it does not move, illustrating inertia. As you apply a force, it accelerates in the direction of your push, demonstrating the second law. When the bicycle's wheels push backward against the ground pushes forward on the wheels, showing the third law in action. In this process, forces interact with mass to produce acceleration. The first law explains why motion does not change without a reason. The second law gives a precise measure of how motion changes. The third law reveals that forces always come in pairs. Together, they form a complete picture of motion, summarized in equations like F equals ma, where F is force, m is mass, and a is acceleration. The implications of these laws extend far beyond simple objects. They explain the motion of planets, the flight of rockets, and even how a swimmer propels through water. Experiments in laboratories and observations in space confirm these principles consistently. They connect to other areas of physics, such as energy, momentum, and even modern engineering. Despite their success, Newton's laws have limitations. They work extremely well at everyday speeds and scales, but at very high speeds or near massive objects, Einstein's theory of relativity provides a more accurate description. Some debates continue about how these laws apply at the quantum level, showing that there are still questions left to explore. Modern research has extended Newton's ideas in fascinating ways. Engineers use these laws to design vehicles, bridges, and spacecraft. Physicists study how forces operate in extreme environments, such as black holes or particle accelerators. Future discoveries may reveal new forms of motion or forces that go beyond classical mechanics. Conceptually, Newton's laws offer more than practical guidance. They reveal a universe governed by predictable patterns and order. Understanding these laws changes the way we see our world, showing that motion is not random but follows principles that can be understood, measured, and applied. In conclusion, Newton's laws of motion explain how objects respond to forces, describing the behavior of everything from everyday objects to celestial bodies. The first law teaches about inertia, the second law links force and acceleration, and the third law shows the reciprocity of forces. Reflecting on these laws, we see not only the beauty of science but the power of human curiosity. They remind us that observation, reasoning, and experimentation can uncover the rules that govern the universe. By studying motion, we not only understand the physical world but also develop the ability to innovate and explore new frontiers. The study of motion invites us to look closely at the forces shaping our world and to consider how our actions interact with the world around us. Every push, pull, and movement tells a story, and Newton's laws give us the language to read it. Law of Universal Gravitation. Have you ever wondered why an apple falls from a tree or why the moon never drifts away from the earth? The law of universal gravitation explains these everyday wonders and much more. It is one of the fundamental laws that govern how objects interact in the universe. Understanding this law helps us make sense of planetary motions, tides, and even the trajectories of satellites. At its core, the law of universal gravitation states that every object in the universe attracts every other object with a force that depends on their masses and the distance between them. This attraction is always present, no matter how far apart objects are. The greater the mass of an object, the stronger its pull. Conversely, the farther apart two objects are, the weaker the gravitational force between them. The key components of this law are mass, distance, and the gravitational constant, which quantifies the strength of this universal force. The idea of gravity has a long history. Ancient thinkers noticed that objects fall to the ground, but they did not fully understand why. It was Isaac Newton, in the 17th century, who formulated the law that explains this attraction in mathematical terms. Newton's work built on observations by earlier astronomers such as Kepler and Galileo, who studied planetary motion and free fall. Milestones in the development of the law include Newton publishing his Principia Mathematica, where he described the mathematical principles of gravitational force and showed that the same force that pulls an apple down also governs the motion of the moon around the Earth. Gravity works through a simple yet powerful mechanism. Consider two objects in space. Each object exerts a pull on the other, directed along the line connecting their centers. The force can be calculated using the formula F equals G times m1 times m2 divided by r squared, where F is the gravitational force, G is the gravitational constant, m1 and m2 are the masses of the objects, and r is the distance between them. This force causes objects to move toward each other, creating interactions we can observe as falling objects, orbiting planets, or even the tides in the ocean. The dynamics of gravity govern not only earthbound phenomena but also the movements of stars, galaxies, and clusters across the universe. The implications of universal gravitation are immense. On a physical level, it explains why planets orbit the Sun and why the Moon orbits the Earth. It allows scientists to predict the paths of comets and artificial satellites with remarkable accuracy. Observational evidence, such as the precise motion of planets and the behavior of tides, supports the universality of this force. Moreover, the law of gravitation connects closely with other areas of physics. For example, it laid the groundwork for Einstein's theory of general relativity, which expands on Newton's ideas to describe how massive objects warp space and time. Despite its success, the law of gravitation faces challenges and open questions. Newton's theory assumes that gravity acts instantaneously across distances, but modern physics suggests that changes in gravity propagate at the speed of light. There are debates and discussions about gravity at very small scales, such as in quantum mechanics, where the behavior of gravitational forces is still not fully understood. Unresolved problems include the nature of dark matter and dark energy, which appear to affect gravitational interactions on cosmic scales but remain mysterious. Modern research continues to explore the applications and limits of gravity. Recent discoveries, such as the detection of gravitational waves, confirm that massive objects like black holes and neutron stars can produce ripples in the fabric of spacetime. Practical applications of gravitational knowledge include designing space missions, calculating satellite orbits, and understanding Earth's climate and tides. Future directions may involve unifying gravity with quantum mechanics, exploring deep space phenomena, or even harnessing gravitational effects in new technologies. From a philosophical perspective, the law of universal gravitation offers profound insight. It shows that the same physical principles apply to objects on Earth and in the farthest reaches of space. Gravity connects the cosmos and our everyday experiences, reminding us of the hidden forces that shape reality. It changes our view of the universe by revealing that everything is interconnected, bound together by invisible forces, and subject to predictable laws. In conclusion, the law of universal gravitation is a cornerstone of physics that explains why objects move as they do. From the falling apple to orbiting planets, it governs the universe with simplicity and elegance. Its historical development, practical applications, and ongoing research highlight the enduring importance of understanding gravitational forces. Studying gravity encourages curiosity, reflection, and a deeper appreciation of the natural world, inspiring us to continue exploring the mysteries of the cosmos. Conservation of energy. Energy is all around us. From the sunlight that warms the earth to the electricity that powers our homes, energy shapes every aspect of our lives. It moves, transforms, and fuels the world, yet there is a remarkable rule that governs it quietly and consistently. This rule is known as the conservation of energy. Understanding this principle is like holding a key to the hidden order of nature. It explains why things happen the way they do and why some processes are inevitable. Energy is the ability to do work or cause change. It can appear as motion, heat, light, chemical changes, or even sound. The principle of conservation of energy tells us that energy cannot be created or destroyed, it can only change from one form to another. This means that the total amount of energy in a closed system always remains the same. Recognizing this law helps us predict outcomes, design technologies, and understand natural events. Without it, the world would seem chaotic and unpredictable. The concept of energy conservation might seem obvious today, but it took careful observation and thought to reach this understanding. Long ago, scientists noticed that while energy could change its form, the total quantity remained steady. They began to see patterns in motion, heat, and light that pointed to a hidden order. Appreciating this concept shows us that nature is not random but follows deep rules that can be studied and understood. At its core, the conservation of energy states that energy in an isolated system remains constant over time. Basic principles include the transformation of energy from kinetic to potential, mechanical to thermal, or chemical to electrical, while the total energy stays unchanged. Key components involve identifying all forms of energy in a system, accounting for energy transfers, and understanding that losses, such as friction or heat, do not destroy energy but convert it into other forms. The history of energy conservation traces back to classical physics. Early thinkers like Galileo and Newton laid the groundwork by studying motion and forces. Later, scientists such as James Joule and Hermann von Helmholtz explored the quantitative aspects of energy, demonstrating through experiments that heat and mechanical work were interchangeable. Milestones included Joule's experiments measuring the mechanical equivalent of heat and Helmholtz's formal statement of energy conservation in the 19th century, which set the stage for modern physics. Energy transformation works in a clear, step-by-step process. When an object moves, potential energy converts into kinetic energy. When it stops, kinetic energy may turn into heat or sound. These interactions are constant in nature. For example, when we roll a ball down a slope, the stored potential energy at the top gradually becomes motion energy, then dissipates slightly as heat due to friction. The key law guiding these changes is expressed mathematically as the total energy at the start equals the total energy at the end plus any energy transferred in or out. The implications of energy conservation are vast. Physically, it governs how machines work, how planets move, and how living organisms sustain themselves. Observational evidence, such as pendulum motion, bouncing balls, or energy calculations in engines, consistently confirms that energy is never lost, only transformed. This principle connects to other areas of physics, including thermodynamics, mechanics, and electromagnetism, showing that energy acts as a universal currency in nature. Despite its clarity, the principle faces challenges. Current limitations arise when dealing with complex systems, such as quantum particles or black holes, where defining energy precisely can be difficult. Debates continue about energy at the smallest scales or in extreme gravitational fields, and unresolved problems remain in fully understanding how energy conservation interacts with relativity and quantum mechanics. These questions push scientists to think deeper and refine our understanding of nature. Modern research has expanded energy conservation into new frontiers. Discoveries in renewable energy, superconductors, and particle physics show practical applications of energy principles. Engineers use these ideas to design engines, electrical grids, and efficient buildings, while scientists explore how energy behaves in the universe at the smallest and largest scales. Future directions include improving energy efficiency, harnessing alternative energy sources, and uncovering the energy mechanisms of the cosmos, offering both practical and theoretical progress. Conceptually, the conservation of energy invites us to reflect on the universe as a balanced system. It teaches that no effort is wasted, no energy disappears, and all change is a transformation. This perspective shifts our view from seeing events as isolated to understanding them as interconnected, revealing the profound order underlying the cosmos. By studying energy, we realize that even the smallest actions ripple through the system, shaping outcomes in ways we may not immediately notice. In conclusion, energy is never lost, only transformed. From the earliest experiments to modern applications, the principle of conservation of energy remains central to understanding nature. It guides scientists, engineers, and thinkers, showing that the universe operates according to consistent rules. Reflecting on this law encourages curiosity, careful observation, and a sense of wonder at the interconnectedness of all things. By embracing this understanding, we not only comprehend the workings of the physical world but also gain insight into the harmony that governs existence. Exploring energy further promises discoveries that can transform our future and deepen our appreciation of the natural world. Conservation of momentum. Imagine two ice skaters gliding towards each other on a frozen lake. They push off, and each moves backward at a certain speed. Something invisible yet powerful governs their motion, keeping track of every ounce of movement. This principle is called the conservation of momentum. It is one of the fundamental ideas in physics that helps us understand how objects interact and move in our universe. Momentum is the product of an object's mass and its velocity. It is a measure of how much motion an object has. The conservation of momentum tells us that in a closed system, where no external forces act, the total momentum remains constant. This simple rule governs collisions, explosions, and many natural phenomena. By studying momentum, we can predict outcomes in sports, engineering, space travel, and even particle physics. Understanding it matters because it connects the microscopic world of atoms to the vast movements of planets. The concept of momentum is rooted in everyday experience. When you catch a ball, when cars collide, or when rockets launch, momentum is being exchanged, transferred, or conserved. It gives us a language to describe motion beyond mere speed. Key principles include that momentum is a vector, meaning it has both magnitude and direction, and that the total momentum of interacting objects before and after an event remains unchanged if no external force interferes. Components like mass, velocity, and the system boundaries play crucial roles in determining the momentum of a body. The history of momentum stretches back to the earliest thinkers of classical mechanics. The idea began with natural philosophers like Galileo, who studied motion and the effects of forces. Later, Sir Isaac Newton formalized the concepts through his 3 laws of motion, providing the framework to understand momentum quantitatively. Another key contributor was Gottfried Wilhelm Leibniz, who introduced the concept of vis viva, or living force, an early form of momentum in mathematical terms. Over time, experiments with colliding balls, pendulums, and cannonballs helped establish the principle as a cornerstone of physics, bridging intuition and calculation. Momentum works through interactions. When 2 objects collide, each exerts a force on the other. These forces are equal and opposite, causing changes in their velocities. To see how this unfolds step by step, imagine 2 carts on a track. Cart A moves towards stationary cart B. When they collide, cart A slows down while cart B speeds up. The total momentum before and after the collision remains the same. Dynamics involve understanding not just speed but direction, mass ratios, and the type of collision, whether elastic or inelastic. The central equation expresses that the sum of all momenta before an interaction equals the sum after, forming a simple yet powerful mathematical law. The implications of momentum conservation are profound. It allows us to predict the results of car crashes, design safer vehicles, and calculate the movements of celestial bodies. Experiments repeatedly confirm this principle, from simple classroom demonstrations to particle accelerators where subatomic particles collide at near light speeds. Momentum also links closely to energy, particularly kinetic energy, showing a deep connection between forces, motion, and the structure of physical laws. It is a bridge that connects mechanics to astrophysics, engineering, and quantum physics, revealing patterns that govern both the large and the small. Despite its reliability, questions and challenges remain. While classical momentum works in everyday life, extreme conditions such as near-light speeds or strong gravitational fields require adjustments using relativity. Debates around momentum in quantum systems, where particles do not have precise positions or velocities, push the limits of our understanding. Certain unresolved problems, like momentum exchange in complex fluids or chaotic systems, highlight the ongoing exploration within modern physics, reminding us that conservation is a principle to be applied carefully depending on context. Modern research continues to expand the applications of momentum. Scientists study momentum transfer in plasmas, laser matter interactions, and nanotechnology. Rockets rely on momentum conservation to navigate space, while particle colliders observe how momentum is distributed among emerging particles. Practical applications include vehicle safety design, sports analytics, and robotics, where momentum calculations help predict movements and improve efficiency. Future directions may involve new forms of propulsion, better understanding of quantum momentum, and deeper insights into energy-momentum relationships in the universe. Beyond practical use, momentum offers a philosophical perspective. It reminds us that the universe follows consistent rules, where actions have measurable consequences and interactions shape outcomes. This principle encourages us to see connections between phenomena, understanding that what is lost in one place is gained elsewhere. It changes our view of the universe, emphasizing balance, predictability, and the interdependence of objects, large and small, near and far. In conclusion, conservation of momentum is more than a formula, it is a guiding principle of nature. It defines how objects move, collide, and interact, providing clarity to both everyday experiences and cosmic events. By exploring its history, mechanisms, and applications, we see a law that is reliable yet invites curiosity. Understanding momentum encourages reflection on balance, causality, and the hidden rules of motion. Observing its effects inspires us to ask deeper questions, experiment boldly, and appreciate the elegant order underlying the universe. Thermodynamics. Thermodynamics is a branch of physics that studies heat, energy, and how they move and change. It is fascinating because it explains why ice melts, why engines work, and why the universe behaves the way it does. From everyday activities like boiling water to understanding stars, thermodynamics is everywhere. It matters because it helps us harness energy, predict natural processes, and understand the fundamental limits of what can happen in the physical world. At its core, thermodynamics is about energy. Energy can neither be created nor destroyed, only transformed. The subject revolves around key principles called laws, which explain how energy flows and changes form. There are four main laws: the zeroth, first, second, and third laws. The zeroth law explains temperature and thermal equilibrium, the first law describes conservation of energy, the second law introduces the idea of entropy or disorder, and the third law deals with the behavior of systems as they approach absolute zero. The basic components include heat, work, energy, temperature, and entropy, all interacting to govern physical processes. The origins of thermodynamics trace back to the study of heat engines in the 18th and 19th centuries. Early scientists noticed that engines could not convert all heat into work and that energy seemed to follow certain patterns. Key contributors include Sadi Carnot, who analyzed the efficiency of engines, James Joule, who demonstrated the mechanical equivalent of heat, Rudolf Clausius, who formulated the concept of entropy, and Lord Kelvin, who refined the temperature scale and developed fundamental thermodynamic ideas. Over time, milestones such as the formalization of the first and second laws and the introduction of the third law shaped thermodynamics into a precise and predictive science. Thermodynamics works by examining the flow and transformation of energy. First, one identifies the system and its surroundings. Then, energy exchanges in the form of heat and work are tracked. Heat is energy transferred because of temperature differences, and work is energy transferred by force acting over a distance. Temperature drives the direction of heat flow, while entropy measures the tendency toward disorder. Key equations include the first law, which states that the change in internal energy equals heat added minus work done, and the second law, which shows that entropy of an isolated system never decreases. These laws guide the understanding of engines, refrigerators, and natural processes. The implications of thermodynamics are profound. Physically, it explains why perpetual motion machines are impossible and why energy conversions always have limits. Observational evidence comes from experiments with steam engines, refrigerators, and chemical reactions, all of which follow the laws precisely. Thermodynamics connects deeply to other areas of physics, such as statistical mechanics, quantum mechanics, and cosmology. It allows us to predict the behavior of gases, the formation of stars, and even the fate of the universe. Despite its power, thermodynamics has challenges. Its laws describe averages and ideal conditions, but real systems can be complex and unpredictable. There are debates about the interpretation of entropy and how it applies to the universe as a whole. Unresolved problems include the thermodynamics of black holes and the detailed behavior of systems far from equilibrium, which remain active areas of research. Modern research continues to explore thermodynamics in new ways. Scientists study nanoscale systems where classical rules merge with quantum effects. Practical applications include engines, power plants, refrigeration, and climate modeling. Advances in understanding energy efficiency, renewable energy, and entropy management have direct impacts on technology and sustainability. Future directions may involve controlling energy at the molecular level, improving battery efficiency, and exploring the thermodynamics of living systems. Thermodynamics also offers philosophical insight. It reminds us that energy and order are limited, that every process has a cost, and that the universe tends toward balance and change. It shapes our understanding of time, since entropy provides a direction from past to future. This perspective encourages reflection on the impermanence of systems and the beauty of natural order. Thermodynamics changes our view of the universe by showing that everything is connected through energy transformations, and that even the smallest processes follow universal principles. In conclusion, thermodynamics teaches us about energy, heat, work, and the laws that govern them. It has a rich history, well-defined principles, and practical applications that touch daily life and advanced science alike. The laws guide us in understanding engines, the cosmos, and the limits of what is possible. Reflecting on thermodynamics inspires awe at the order within nature and encourages further exploration of how the universe works. By studying thermodynamics, we gain not only knowledge but also a deeper appreciation of the forces shaping our world and our place within it. Electromagnetism. Electromagnetism is one of the most fascinating and fundamental aspects of physics. Imagine a world without electricity, without lights, motors, or even the invisible forces that allow your phone to work. This topic explores the invisible connections between electric and magnetic forces and how they shape the world around us. Understanding electromagnetism helps us not only grasp the behavior of nature but also develop technologies that have transformed human life. At its core, electromagnetism describes the interaction between electric charges and magnetic fields. It explains how moving charges create magnetic fields, how changing magnetic fields induce electricity, and how these forces influence matter. The basic principles rely on the existence of electric fields, magnetic fields, and the way they interact with charged particles. Key components include electric charge, electric current, magnetic flux, and the fundamental constants that govern their interactions. The story of electromagnetism began centuries ago. Early scientists like William Gilbert studied static electricity and magnetism. Later, Hans Christian Ørsted discovered that electric currents produce magnetic effects, revealing a deep connection between electricity and magnetism. André-Marie Ampère formulated laws describing the force between electric currents. Michael Faraday demonstrated electromagnetic induction, showing that a changing magnetic field can create an electric current. All these discoveries culminated in James Clerk Maxwell's elegant equations, which united electricity, magnetism, and light under a single framework. Electromagnetism works through clear mechanisms. A step-by-step view begins with a stationary charge, which produces an electric field. When the charge moves, it generates a magnetic field around its path. If a magnetic field changes near a conductor, it induces an electric current in the conductor. This interaction forms the basis of generators, motors, and transformers. Electric and magnetic fields are deeply connected, influencing each other in predictable ways. Maxwell's equations express these relationships mathematically. Gauss's law explains how electric charges produce electric fields. Gauss's law for magnetism shows that magnetic monopoles do not exist. Faraday's law describes how changing magnetic fields induce electric currents. Ampère-Maxwell law links electric currents and changing electric fields to magnetic fields. Together, these equations describe the dynamic dance of electromagnetism. The implications of electromagnetism are profound. Physically, it governs the behavior of light, radio waves, and all electromagnetic radiation. Theoretically, it unites electricity and magnetism into a single framework, revealing the deep symmetry of nature. Experiments confirm these laws repeatedly, from simple circuits in the classroom to advanced particle accelerators. Electromagnetism connects to many areas of physics, including optics, quantum mechanics, and relativity. Without understanding it, modern science and technology would be impossible. Despite its clarity, electromagnetism still presents challenges. Classical descriptions break down at atomic and subatomic scales, requiring quantum electrodynamics to explain interactions precisely. Some debates continue over the nature of magnetic monopoles, and researchers are exploring the limits of electromagnetic wave manipulation. Questions remain about how electromagnetism interacts with gravity and whether undiscovered phenomena could expand our understanding of the universe. These open problems invite curiosity and exploration. Modern research in electromagnetism continues to yield remarkable discoveries. Scientists study advanced materials, like superconductors and metamaterials, which interact with electromagnetic fields in novel ways. Technologies based on these principles are everywhere: electric motors, wireless communication, medical imaging, and renewable energy systems all rely on electromagnetism. Theoretical studies explore faster computing, new energy sources, and ways to control electromagnetic waves at tiny scales. The future promises even more applications that could change daily life and expand our scientific horizons. Electromagnetism also offers philosophical insights. It shows that invisible forces govern the universe, and that mathematics can reveal hidden truths about nature. Maxwell's equations suggest a universe that is interconnected and predictable, yet filled with mystery. By studying electromagnetism, we learn that the world operates through patterns that we can observe, understand, and use. It invites reflection on the beauty of natural laws and the power of human curiosity to uncover them. In conclusion, electromagnetism is a cornerstone of physics that explains how electric and magnetic forces interact. From early experiments with static electricity to Maxwell's unifying equations, it has shaped our understanding of light, energy, and matter. The study of electromagnetism has led to countless technologies that define modern life and continues to inspire research at the cutting edge of science. By exploring these forces, we not only understand the physical world but also connect to a deeper sense of wonder about how the universe works. This knowledge encourages us to keep questioning, exploring, and discovering, as the invisible currents of electromagnetism guide both nature and human progress. Wave theory of light. Light has fascinated humans for centuries. Its ability to illuminate the world around us and reveal the hidden beauty of nature makes it one of the most remarkable phenomena. From the rainbow in the sky to the glow of a candle, light shapes our experiences in ways we often take for granted. Understanding its nature has been a key pursuit in science. Wave theory of light provides one of the most profound explanations of this phenomenon, showing us that light behaves like a wave, spreading and interacting with the world in predictable patterns. The study of light matters because it is essential to almost every aspect of our lives. It allows us to see, to communicate through technologies like fiber optics, and to explore the universe through telescopes. By studying light as a wave, scientists have been able to explain patterns and behaviors that were once mysterious, such as the formation of colors, reflection, refraction, and interference. Wave theory defines light as a form of energy that travels in waves. These waves are not like water waves that move up and down visibly, but they involve oscillations of electric and magnetic fields as they travel through space. The basic principle of wave theory is that light exhibits properties such as diffraction, interference, and polarization, which are characteristic of waves. The key components of a light wave include its wavelength, which measures the distance between peaks of the wave, its frequency, which counts the number of oscillations per second, and its amplitude, which determines the intensity of the light. The origins of the wave theory of light trace back to the 17th century. Early ideas about light were often debated, with some believing it was made of tiny particles while others suggested it had wave-like qualities. The key contributors to wave theory include Christian Huygens, who proposed that every point on a wavefront acts as a source of new waves, and Thomas Young, whose famous double-slit experiment provided clear evidence of light interference. Augustin-Jean Fresnel later refined the theory, showing mathematically how light waves interact and form patterns. These milestones gradually convinced the scientific community that light could be understood as a wave. The mechanism of wave propagation explains how light moves through space. Light travels in oscillating waves of electric and magnetic fields that are perpendicular to each other and to the direction of motion. Step by step, a wavefront progresses, spreading energy across space. When light encounters obstacles or openings, it bends around them in a process called diffraction. When two waves meet, they can combine constructively to increase intensity or destructively to cancel each other out, creating interference patterns. Key equations describe these behaviors, such as the wave equation, which relates wavelength, frequency, and the speed of light, and the principle of superposition, which explains interference. The implications of wave theory are profound. Physically, it allows us to predict and explain phenomena like rainbows, mirages, and the colors produced by thin films. Experimentally, observations such as Young's double-slit experiment and Fresnel's diffraction studies provide solid evidence that light behaves as a wave. The theory also connects to other areas of physics, including electromagnetism, quantum mechanics, and optics, offering a unified understanding of energy propagation and interactions. Despite its successes, wave theory also faces challenges. It cannot fully explain certain phenomena like the photoelectric effect, where light striking a metal surface ejects electrons, an observation that led to the development of quantum theory. Some debates continue about the exact nature of light and the relationship between its wave and particle properties. Unresolved questions include the detailed mechanisms of light-matter interaction and how classical wave descriptions fit with modern quantum explanations. Modern research and applications of wave theory are extensive. Recent discoveries involve precise control of light waves in technologies such as lasers, holography, and optical fibers. Practically, understanding light as a wave has led to innovations in communication, medicine, and imaging. In theoretical physics, wave concepts are essential for studying electromagnetic radiation, wave-particle duality, and the behavior of light in complex media. Future directions include manipulating light waves for quantum computing, advanced microscopy, and exploring the limits of wave-based technologies. Wave theory also offers deep philosophical insight. It shows that what we perceive as a simple beam of light is part of a complex, dynamic process governed by patterns and interactions. This perspective encourages us to see the universe as interconnected, where even everyday phenomena reveal underlying order and beauty. By studying light waves, we gain a glimpse into the hidden structure of reality and the principles that govern energy, matter, and motion. In conclusion, wave theory of light provides a rich and powerful explanation of one of nature's most important phenomena. It helps us understand how light travels, interacts, and influences the world. By tracing its historical development, exploring its mechanisms, and observing its consequences, we gain both practical knowledge and philosophical perspective. Light, once a mysterious force, becomes a window into the workings of the universe. The study of waves encourages curiosity and reminds us that there is always more to discover, not only about light but about the vast and intricate cosmos in which we live. Special relativity. Special relativity is a theory in physics that explains how space and time behave when objects move very fast, close to the speed of light. It shows that time can slow down, lengths can contract, and mass can increase depending on how fast something is moving. This idea may sound strange, but it connects to everyday reality in ways we might not notice. For example, GPS satellites rely on corrections from special relativity to give accurate location readings. Without accounting for these effects, our maps and navigation systems would be wrong by several kilometers. The origins of special relativity trace back to the late 19th and early 20th centuries. Scientists were trying to understand the behavior of light and how it travels through space. James Clerk Maxwell had formulated equations describing electricity and magnetism, showing that light is an electromagnetic wave. However, these equations did not fit well with Newtonian mechanics when it came to moving objects. Albert Einstein, in 1905, introduced a new framework that resolved these contradictions. Other key scientists who contributed ideas included Hendrik Lorentz and Henri Poincaré, whose work on transformations and the nature of space and time laid the groundwork for Einstein's revolutionary ideas. Before special relativity, physics was dominated by Newton's laws. These laws assumed that time and space were absolute, the same for everyone, everywhere. However, experiments with light and electromagnetic waves revealed inconsistencies. For example, the famous Michelson-Morley experiment failed to detect any motion of the Earth through a supposed ether, a medium for light waves. These contradictions showed that the old ideas could not explain the true behavior of light and motion. A new framework was needed to reconcile these conflicts and accurately describe the universe at high speeds. Einstein based his theory on two central principles. First, the laws of physics are the same for all observers who are moving at constant speeds. Second, the speed of light in a vacuum is constant for all observers, no matter how they or the light source are moving. These assumptions challenge the traditional view that time and space are fixed. Instead, time can pass differently for different observers, and distances can appear shorter depending on motion. These postulates form the foundation of special relativity and lead to its most surprising conclusions. Mathematically, special relativity relies on transformations called Lorentz transformations. These equations show how space and time coordinates change between observers moving relative to each other. Another important concept is the idea of spacetime, a combined four-dimensional continuum of space and time. Energy and mass are connected through the famous equation E equals mc squared, which shows that mass can be converted into energy and vice versa. These concepts allow scientists to calculate how moving objects behave at speeds close to light and predict effects that were previously unimaginable. Special relativity predicts several remarkable phenomena. Time dilation explains that a clock moving at high speed ticks slower compared to one at rest. Length contraction shows that objects shrink along the direction of motion as they move faster. Relativistic mass increase means that an object's mass appears to grow as its speed approaches the speed of light. These predictions challenge everyday intuition but have been repeatedly confirmed through observation and experimentation. They help explain why particles and accelerators behave differently than everyday objects and why cosmic rays interact with the atmosphere in specific ways. Experimental evidence for special relativity is abundant. The Michelson-Morley experiment was an early hint that the classical ideas were incomplete. Later, precise tests using atomic clocks on airplanes confirmed time dilation. Particle accelerators routinely observe mass increase and relativistic effects as particles reach near light speeds. Observations of fast-moving stars and cosmic rays also matched the predictions of special relativity. These experiments provide strong confirmation that Einstein's theory accurately describes the behavior of nature at high velocities. Special relativity has had a profound impact on technology and science. It is essential for the proper functioning of GPS systems, particle accelerators, and even modern electronics. Scientifically, it transformed our understanding of space, time, energy, and matter. It opened the door to general relativity, which explains gravity as the curvature of spacetime, and has influenced countless fields from cosmology to quantum physics. Its applications go far beyond theory, affecting everyday life in ways we often take for granted. Philosophically, special relativity changed the way humanity views reality. It showed that space and time are not separate and absolute but intertwined and relative. The idea that observers experience reality differently depending on their motion challenges the notion of a single, universal time. This shift in perspective encourages deeper reflection on the nature of existence, the limits of human perception, and the structure of the universe itself. Modern developments continue to explore special relativity in extreme conditions. Scientists study relativistic effects in high-energy astrophysics, near black holes, and in particle collisions at the largest accelerators. Open questions remain about how relativity interacts with quantum mechanics and whether new physics will emerge at even higher energies. Researchers are also investigating potential small deviations from relativity that could reveal new insights into the fundamental laws of nature. In summary, special relativity teaches us that time and space are flexible and depend on motion. It resolves inconsistencies in classical physics, predicts counterintuitive phenomena like time dilation and length contraction, and is confirmed by extensive experimental evidence. It has practical applications in technology and deep implications for how we understand the universe. As we continue to explore the cosmos and push the boundaries of speed and energy, special relativity reminds us that reality is stranger and more beautiful than everyday experience suggests. Our understanding of time, space, and motion is no longer fixed but a dynamic tapestry that invites curiosity and wonder. General relativity. General relativity is a theory of gravitation that explains how massive objects influence space and time. It describes gravity not as a force but as the bending of spacetime caused by mass and energy. In everyday life, this idea explains why objects fall to the ground, how planets orbit the sun, and even why GPS systems need precise adjustments to work correctly. It shows that the universe is a dynamic fabric where matter and energy shape the very space through which they move. The origin of this theory dates back to the early 20th century when scientists began questioning the limits of Newtonian physics. Isaac Newton had described gravity as a force acting at a distance, but certain observations, like the orbit of Mercury, did not fully match his predictions. Albert Einstein developed general relativity between 1907 and 1915, building on his earlier work on special relativity. Other key scientists, including Henri Poincaré and David Hilbert, contributed to refining the mathematical framework, but Einstein was the mind who unified these ideas into a new understanding of gravity. Before general relativity, Newtonian mechanics was widely accepted, but it could not explain phenomena involving very large masses, high speeds, or strong gravitational fields. Mercury's orbit showed slight irregularities, and light bending near massive objects was unexplained. A new framework was needed to describe these extreme conditions accurately and to reconcile gravity with the principles of special relativity. The central postulates of general relativity are that the laws of physics are the same for all observers, regardless of their motion, and that gravity is the result of the curvature of spacetime caused by mass and energy. It assumes that space and time are not separate entities but part of a single continuum. This means that objects follow paths called geodesics, which are the straightest possible lines in curved spacetime. The mathematical framework of general relativity relies on Einstein's field equations. These equations describe how mass and energy determine the curvature of spacetime. Essential concepts include spacetime curvature, geodesics, and the equivalence principle, which states that the effects of gravity and acceleration are locally indistinguishable. The geometry of spacetime can be visualized as a flexible fabric that bends under the weight of objects, influencing how other objects move. General relativity predicts several unique behaviors of the universe. It explains the bending of light around massive objects, known as gravitational lensing, and the slowing of time near strong gravitational fields, called time dilation. The theory also predicts the existence of black holes, regions where spacetime curvature becomes infinite, and gravitational waves, ripples in spacetime caused by accelerating masses. These phenomena demonstrate the richness of the universe beyond everyday experience. Experimental evidence has repeatedly confirmed general relativity. One of the earliest tests was the observation of starlight bending during a solar eclipse in 1919, which matched Einstein's predictions. Later, precise measurements of Mercury's orbit and the detection of gravitational waves in 2015 by the LIGO Observatory provided strong support. Modern technology, such as satellite-based GPS, requires corrections based on general relativity to maintain accuracy, further confirming its real-world relevance. The applications and impact of general relativity extend beyond theoretical physics. It is essential for understanding cosmology, black holes, and the evolution of the universe. Technologically, it is critical in satellite navigation, astronomy, and space exploration. Scientifically, it has reshaped our understanding of gravity, showing that space and time are dynamic and interconnected with matter and energy. General relativity also has profound philosophical implications. It challenges our intuitive sense of space and time as fixed backgrounds and reveals that reality is influenced by the presence of matter and energy. The theory encourages a deeper reflection on the nature of the universe, the limits of human perception, and the interconnectedness of all things. It shifts our view from a simple mechanical universe to a complex and dynamic cosmos. Modern developments in general relativity explore extreme conditions such as the interiors of black holes and the early universe near the Big Bang. Researchers are investigating how gravity interacts with quantum mechanics, seeking a theory of quantum gravity. Questions about dark matter, dark energy, and the ultimate fate of the universe remain open, making general relativity a living and evolving field of study. In summary, general relativity is a revolutionary theory that describes gravity as the curvature of spacetime. It replaced Newtonian ideas for extreme conditions, predicted phenomena like black holes and gravitational waves, and has been confirmed through numerous experiments. Its principles continue to guide scientific research and technological applications, showing the universe as a dynamic and interconnected fabric. Reflecting on general relativity, it invites us to see the universe in a new light, where space and time are not mere stages for events but active participants in the cosmic story. It reminds us that science is not just a collection of facts but a way of understanding the hidden order of reality and the profound connections that shape our world. Quantum mechanics. Quantum mechanics is a branch of physics that explains how tiny particles like electrons and photons behave. Unlike the objects we see every day, these particles do not follow the simple rules of classical physics. The Schrödinger equation is at the heart of quantum mechanics. It allows scientists to predict the probability of where a particle might be and how it moves. In everyday life, quantum mechanics is behind technologies like semiconductors, lasers, and MRI machines. Even the screens of our phones rely on principles that come from this strange but powerful theory. The origin of quantum mechanics began in the early 20th century when classical physics could not explain certain experiments. Scientists like Max Planck, who studied blackbody radiation, laid the groundwork. Albert Einstein contributed with his explanation of the photoelectric effect, and Niels Bohr proposed models of the atom. Erwin Schrödinger, in 1925, formulated an equation that described particles as waves, uniting many earlier ideas into a single framework. Classical physics assumed that particles had precise positions and velocities, but experiments showed that this was not true at microscopic scales. Atoms emitted light in specific patterns, and electrons did not orbit the nucleus like planets. There was a need for a new framework that could explain the probabilistic and wave-like behavior of matter. Schrödinger's work provided a tool that could describe these behaviors mathematically and conceptually. The central postulates of the Schrödinger equation include the idea that particles are represented by wave functions. These wave functions contain all the information about the system and evolve over time according to the Schrödinger equation. A key assumption is that energy and momentum are quantized at small scales, meaning they can only take certain discrete values. Another assumption is that the universe at the microscopic level behaves according to probabilities rather than certainties. The Schrödinger equation itself is written as a mathematical formula that relates the energy of a particle to its wave function. In simple terms, it shows how the shape of a particle's wave function changes over time. Essential concepts include superposition, where a particle can exist in multiple states at once, and probability density, which describes where a particle is most likely to be found. These concepts are very different from everyday experience but have been tested and confirmed in many experiments. The equation predicts several unique behaviors. Particles can tunnel through barriers that seem impossible to cross. Atoms have discrete energy levels, which explain the colors of light emitted by different elements. Electrons do not spiral into the nucleus because their wave-like nature creates stable patterns. These predictions were completely new and could not be explained by classical physics. Experimental evidence supporting the Schrödinger equation comes from several landmark experiments. The double-slit experiment demonstrated the wave nature of electrons. Spectroscopy showed that atoms emit light in discrete lines, matching the energy levels predicted by the equation. More recently, experiments with quantum dots and superconducting circuits confirmed the probabilistic and wave-like properties of particles, consistent with Schrödinger's theory. Quantum mechanics has many applications. It underpins modern electronics, including transistors and integrated circuits. Lasers, which rely on controlled energy levels of atoms, are used in communication and medicine. Understanding chemical reactions at the quantum level has revolutionized chemistry and materials science. Scientifically, it is important because it provides a complete and accurate description of microscopic processes, which was impossible with classical theories. The Schrödinger equation also changes how we think about reality. It challenges the idea that everything is predictable. Instead, the universe at its smallest scale is inherently probabilistic. This forces us to reconsider the nature of knowledge, determinism, and even reality itself. It shows that observation and measurement play a fundamental role in shaping what we can know about the world. Modern developments in quantum mechanics explore new phenomena and technologies. Quantum computing aims to use superposition and entanglement to perform calculations far faster than classical computers. Quantum cryptography promises secure communication based on fundamental principles of physics. Open questions include how quantum mechanics connects with gravity and how to fully interpret the meaning of the wave function. In summary, the Schrödinger equation is a cornerstone of quantum mechanics. It describes particles as waves, predicts discrete energy levels, and explains behaviors that classical physics could not. It has transformed both technology and our understanding of the microscopic world. By uniting probability and waves, it allows us to explore the universe in ways that were once unimaginable. Looking forward, quantum mechanics invites us to imagine a universe that is far stranger than everyday experience. The Schrödinger equation is not just a tool for scientists, it is a window into the fundamental workings of nature. As research continues, we may discover new laws and technologies that will reshape our understanding of reality itself. Quantum electrodynamics, often called QED, is the theory that describes how light and matter interact. It is the part of physics that explains how tiny particles like electrons and photons behave and affect each other. QED shows that particles can exchange energy in the form of light, and this exchange follows precise mathematical rules. In everyday life, QED helps us understand why electricity flows in wires, why light reflects off mirrors, and why lasers work. It also explains the behavior of atoms and molecules, which are the building blocks of everything around us, from the air we breathe to the screens we use. The story of QED begins in the early 20th century, when scientists were struggling to understand the strange behavior of light and electrons. Classical physics, which had explained motion and forces for centuries, could not fully describe these tiny particles. The origin of the theory came from efforts to combine quantum mechanics, which describes the rules of the very small, with electromagnetism, which describes electric and magnetic forces. Several brilliant scientists contributed to the development of QED. Paul Dirac first proposed a mathematical model for electrons and their interaction with light. Richard Feynman, Julian Schwinger, and Shinichiro Tomonaga later refined the theory, making it consistent and able to produce accurate predictions. Before QED, physicists faced serious problems in explaining how light and matter interact. Classical ideas could not explain why electrons did not spiral into the nucleus of an atom or why atoms emitted only certain colors of light. The predictions often gave infinite results that made no sense. A new framework was needed to solve these problems, to create a theory that could handle both the strange rules of quantum mechanics and the forces of electricity and magnetism in a single, reliable framework. The fundamental principles of QED rest on a few key ideas. At the center is the concept that particles, like electrons, can emit and absorb photons, which are particles of light. This exchange governs all electromagnetic interactions. Another central postulate is that probabilities, rather than certainties, determine how these interactions occur. This means that we can calculate the likelihood of an event, like an electron scattering off another electron, but not predict the exact moment it will happen. QED also assumes that space and time obey the rules of special relativity, ensuring that the theory works even at very high speeds and energies. Mathematically, QED is built on complex equations known as quantum field theory. The core equations describe the behavior of electrons, positrons, and photons, and how they interact. One important concept is the Feynman diagram, which allows scientists to visualize interactions as lines and vertices, showing how particles exchange photons. The idea of virtual particles, which exist temporarily during interactions, is another essential concept. These mathematical tools make QED one of the most accurate theories in science, predicting outcomes with astonishing precision. QED explains several key phenomena that affect both science and technology. It predicts the tiny shifts in energy levels of electrons within atoms, known as the Lamb shift. It also explains the magnetic moment of the electron, which measures how the electron reacts to magnetic fields. These predictions have been confirmed through experiments and are unique behaviors that classical physics could not account for. QED also describes the way light interacts with matter, leading to technologies like lasers and semiconductors. The experimental evidence for QED is strong and convincing. Landmark experiments, such as precision measurements of the electron's magnetic moment and the Lamb shift, have matched QED predictions to an extraordinary degree. Observations of particle collisions in laboratories and measurements of atomic spectra provide further confirmation. These experiments show that QED is not only a mathematical theory but also a real description of the world at the smallest scales. QED has many applications and a wide impact. Technologically, it underpins the development of electronic devices, lasers, and even quantum computers. Scientifically, it is a cornerstone of modern physics, connecting the principles of quantum mechanics with electromagnetic forces. Without QED, we could not fully understand atomic structures, chemical reactions, or the behavior of light in advanced optical systems. The conceptual and philosophical implications of QED are profound. It changes our understanding of reality by showing that the world at the smallest scales is governed by probabilities and interactions that cannot be seen directly. It challenges our classical intuition and teaches us that the universe is far more subtle and interconnected than everyday experiences suggest. Conceptual shifts brought by QED encourage us to think beyond simple cause and effect, understanding that the universe operates on rules that are both precise and counterintuitive. Modern developments in QED continue to push the boundaries of knowledge. Current research explores how QED interacts with other forces of nature, how it can be applied in extreme conditions like near black holes, and how it can help develop new quantum technologies. Open questions remain, including how QED connects with gravity and how its principles might be extended to explain unknown phenomena in particle physics. In summary, QED teaches us that light and matter interact through a precise set of rules, with probabilities governing every event. The theory solves problems that classical physics could not, provides accurate predictions confirmed by experiments, and enables technological advances. Its principles reveal a universe governed by subtle interactions and deep mathematical laws. As we reflect on QED, we see a universe that is both strange and beautiful. It reminds us that even the smallest particles follow patterns that shape everything around us. The study of QED encourages curiosity, challenges assumptions, and opens the door to discoveries that continue to transform both science and our understanding of reality. Quantum chromodynamics. Quantum chromodynamics, often abbreviated as QCD, is the theory that explains how quarks and gluons interact to form protons, neutrons, and other particles. It is a fundamental part of particle physics and helps us understand the forces that hold the nuclei of atoms together. While these particles are extremely small and not visible to the naked eye, the forces described by QCD shape the structure of all matter around us. From the stability of the atoms in our bodies to the energy released in stars, quantum chromodynamics connects the microscopic world of quarks to the everyday reality we experience. The story of quantum chromodynamics began in the 1960s and 1970s when physicists were trying to understand the strong force, one of the four fundamental forces of nature. The need for a new theory arose because existing models, such as the older idea of meson exchange, could not fully explain why atomic nuclei were so stable despite the repulsive forces between protons. Researchers like Murray Gell-Mann and George Zweig introduced the idea of quarks as the building blocks of matter. Later, theoretical work by David Gross, Frank Wilczek, and David Politzer showed that quarks interact through a force that becomes weaker at very short distances and stronger at larger separations. Their work laid the foundation for quantum chromodynamics as the correct theory of the strong interaction. Before QCD, physicists struggled with several limitations. Models could not explain why quarks were never observed as free particles or why the strong force behaved so differently from electromagnetism. These problems required a framework that could account for confinement, the phenomenon that binds quarks together, and asymptotic freedom, where quarks behave as nearly free particles at high energies. A new theory was needed to unify these observations and provide a consistent mathematical explanation for the strong force. At the heart of quantum chromodynamics are a few fundamental principles. The theory proposes that quarks carry a property called color charge, which comes in three types: red, green, and blue. Gluons are the particles that mediate the strong force between quarks, similar to how photons carry the electromagnetic force. A central postulate of QCD is that color charge is always conserved, and that quarks combine in such a way that the resulting particle is color neutral. The theory also assumes that gluons themselves carry color charge, allowing them to interact with each other and create complex behavior within atomic nuclei. Mathematically, quantum chromodynamics is built on the framework of gauge theory, specifically using the symmetry group known as SU(3). The key equations of QCD are based on the interactions between quark fields and gluon fields, which describe how particles exchange force and move over time. Essential concepts include confinement, asymptotic freedom, and the running of the strong coupling constant, which shows how the strength of the strong force changes with energy. These models allow physicists to calculate the masses of particles and predict their interactions with great precision. Quantum chromodynamics makes several important predictions. One major consequence is confinement, which explains why quarks are never found alone but always in groups forming protons, neutrons, and other hadrons. Another prediction is asymptotic freedom, where quarks interact weakly at very high energies, a behavior confirmed in particle accelerators. QCD also explains phenomena like the formation of glueballs, hypothetical particles made entirely of gluons, and the behavior of quark-gluon plasma, a state of matter that existed in the early universe. These unique behaviors demonstrate the power of the theory to describe the inner workings of matter. Experimental evidence for QCD comes from high-energy particle collisions. Landmark experiments at laboratories like CERN and Fermilab have observed jets of particles that match the predictions of quark and gluon interactions. Deep inelastic scattering experiments in the late 1960s and 1970s revealed the point-like structure of protons and neutrons, providing strong evidence for the existence of quarks. Observations of particle masses, decays, and the strong force behavior consistently support the theoretical framework of QCD. Quantum chromodynamics has significant applications and impact. Technologically, understanding the strong force is essential in nuclear energy and particle accelerator experiments. Scientifically, QCD is critical for our knowledge of the universe at its most fundamental level, helping explain how stars shine, how matter formed after the Big Bang, and how atomic nuclei behave. Its influence extends beyond physics, inspiring new mathematical techniques and computational methods in other fields of science. The philosophical implications of quantum chromodynamics are profound. The theory challenges our perception of reality by showing that the visible world is built from invisible particles held together by invisible forces. It forces us to reconsider what it means for something to be a building block of matter and demonstrates that even seemingly empty space is filled with dynamic interactions. This conceptual shift encourages a deeper appreciation of the hidden order and complexity underlying the universe. Modern developments in QCD include studying the behavior of quark-gluon plasma and exploring QCD at extremely high densities, such as those in neutron stars. Researchers are also investigating the structure of exotic hadrons and the role of gluons in binding quarks. Despite the progress, open questions remain, such as the detailed mechanism of confinement and the full spectrum of glueballs. These challenges continue to drive experimental and theoretical research in particle physics. In summary, quantum chromodynamics provides a comprehensive explanation of the strong force and the interactions between quarks and gluons. It resolves the limitations of earlier models, predicts unique behaviors of matter, and has been confirmed through a wide range of experiments. The theory connects the microscopic world to the macroscopic phenomena we observe, offering insights into the fundamental nature of the universe. Quantum chromodynamics reminds us that the world we see is only a small part of a much larger, intricate reality. As we explore deeper into the behavior of matter and energy, we not only learn about the universe but also about the surprising ways in which its smallest components shape everything around us. Understanding QCD is not just about physics, it is a journey into the unseen forces that give structure and life to our cosmos. Standard Model of Particle Physics. The Standard Model of Particle Physics is a theory that describes the fundamental particles and forces that make up the universe, except for gravity. It explains how particles like quarks, electrons, and neutrinos interact through forces such as the electromagnetic, weak, and strong forces. This model helps us understand the building blocks of matter and the rules that govern their behavior. The theory connects to everyday reality because it underlies everything we see and use. The electricity in our homes, the chemical reactions in our bodies, and the technology in our phones and computers all rely on the interactions of these particles. The idea of the Standard Model grew from the need to explain observations that earlier theories could not. In the early 20th century, scientists discovered that atoms were made of smaller components, leading to questions about what held them together. Experiments showed the existence of many new particles, which could not be explained by classical physics alone. Pioneering scientists such as Albert Einstein, Niels Bohr, and later Murray Gell-Mann, Sheldon Glashow, Abdus Salam, and Steven Weinberg contributed to the development of this theory. Their work combined ideas from quantum mechanics and relativity, providing a framework for understanding the subatomic world. Before the Standard Model, scientists faced limitations in describing particles and their interactions. Classical physics could explain motion and forces on a large scale but failed at tiny scales inside atoms. Early quantum theories described some behaviors but could not unify all known particles and forces. A new framework was needed to bring order to a growing list of discoveries and to predict phenomena that experiments could test. The Standard Model is based on a few fundamental principles. It assumes that all matter is made from a set of basic particles divided into quarks and leptons. These particles interact through three fundamental forces, excluding gravity. Central postulates include the idea that forces are mediated by exchange particles called bosons, such as photons for the electromagnetic force, W and Z bosons for the weak force, and gluons for the strong force. Key assumptions also include symmetry principles that help explain conservation laws in particle interactions. The mathematical and conceptual framework of the Standard Model uses quantum field theory. This framework treats particles as excitations in fields that permeate space. Core equations describe how particles interact, scatter, and decay. The Dirac equation explains the behavior of electrons and other fermions, while the Yang-Mills equations describe the force-carrying bosons. Essential concepts include particle families, gauge symmetry, and the Higgs mechanism, which gives mass to particles. The Standard Model makes several key predictions and explains phenomena that were previously mysterious. It predicts the existence of particles like the top quark and the Higgs boson, as well as behaviors such as particle-antiparticle creation and annihilation. Major consequences of the model include understanding nuclear reactions in stars, the stability of matter, and the processes behind radioactive decay. It uniquely explains why some particles interact strongly, others weakly, and some not at all. Experimental evidence has confirmed the predictions of the Standard Model through landmark experiments. The discovery of the W and Z bosons at CERN in the 1980s provided strong support for the theory of weak interactions. The detection of the top quark in 1995 and the Higgs boson in 2012 confirmed the existence of predicted particles. Observational confirmations also come from high-energy particle collisions in accelerators, where the results match theoretical predictions with high precision. The Standard Model has many applications and impacts. Technologically, it underlies the development of particle accelerators, medical imaging, and radiation therapy. Scientific importance lies in providing a unified description of matter and forces, guiding further research in both physics and cosmology. It forms the foundation for understanding phenomena ranging from atomic structure to the evolution of the universe. The theory also has conceptual and philosophical implications. It changes our understanding of reality by showing that matter is not continuous but made of discrete particles with predictable behaviors. Conceptual shifts include the acceptance of fields as fundamental entities and the idea that symmetries govern the laws of nature. It challenges intuitive ideas about space, time, and matter, encouraging deeper reflection on the structure of the universe. Modern developments continue to push the boundaries of the Standard Model. Current research directions include studying neutrino masses, exploring dark matter, and searching for physics beyond the Standard Model, such as supersymmetry or extra dimensions. Open questions remain about why particles have the masses they do and how to unify the Standard Model with gravity. In summary, the Standard Model provides a detailed map of the subatomic world. It identifies the basic particles, describes their interactions, and predicts phenomena that experiments confirm. It unifies a wide range of observations into a coherent framework and forms the foundation of modern physics. Looking forward, the Standard Model represents both achievement and opportunity. While it explains much about the universe, its limitations inspire curiosity and exploration. The journey to understand the fundamental nature of reality continues, reminding us that each discovery opens new doors to the unknown. Statistical Mechanics. Statistical mechanics is a branch of physics that connects the microscopic behavior of particles like atoms and molecules to the macroscopic properties of matter such as temperature, pressure, and volume. It helps us understand how the random motion of countless tiny particles results in the predictable behavior of large systems. This field allows scientists to predict physical properties and understand why materials behave the way they do. The principles of statistical mechanics can be seen in everyday life. For example, when we boil water, the motion of countless water molecules determines the temperature at which it changes from liquid to gas. When a refrigerator keeps food cold, it is the microscopic interactions of molecules that allow heat to be transferred efficiently. Even the weather and the flow of air around us are governed by these statistical laws, showing the connection between tiny particles and the world we experience. The idea of statistical mechanics arose in the 19th century when scientists were trying to explain thermodynamic phenomena using the behavior of atoms and molecules. The theory originated as a response to the need to connect macroscopic laws of heat and energy with the microscopic world. Scientists such as Ludwig Boltzmann and James Clerk Maxwell played key roles in developing the foundations of this theory. Boltzmann introduced the idea that the probability of a system being in a certain state could be described mathematically, while Maxwell formulated the distribution of particle speeds in gases. Their work laid the foundation for understanding the microscopic origins of temperature and pressure, bridging the gap between observations and theory. Before statistical mechanics, classical thermodynamics could explain the relationships between heat, work, and energy, but it could not describe the underlying behavior of individual particles. The limitation of previous ideas was that they treated matter as continuous and ignored the discrete and random nature of atoms and molecules. There was no framework to calculate why heat flows, why gases expand, or why energy is distributed in particular ways. A new approach was needed to account for the statistical nature of large numbers of particles and to explain why systems tend to move toward equilibrium. The fundamental principles of statistical mechanics rest on the connection between microscopic states and macroscopic observables. The central postulates include the idea that a system can occupy many possible microscopic configurations and that each configuration has a certain probability. Systems evolve toward the most probable arrangements, leading to predictable macroscopic behavior. Key assumptions include the existence of a large number of particles, their interactions being governed by known forces, and the concept of ergodicity, which suggests that over time, a system explores all accessible states. The mathematical and conceptual framework of statistical mechanics is built on probability theory and classical or quantum mechanics. Core equations include the Boltzmann distribution, which predicts the probability of a particle having a certain energy, and the partition function, which links microscopic states to thermodynamic properties. Essential concepts such as entropy, temperature, and free energy arise naturally in this framework. Entropy measures the disorder or number of possible states, while temperature reflects the average energy per particle, and free energy determines the direction of spontaneous processes. Statistical mechanics predicts a wide range of phenomena. It explains why gases expand to fill a container, why heat flows from hot to cold objects, and why phase transitions like melting or boiling occur at specific temperatures. Major consequences include understanding the laws of thermodynamics from a microscopic perspective and predicting the behavior of new materials. Unique behaviors such as superfluidity in liquid helium and Bose-Einstein condensation in ultra-cold gases can only be explained through statistical mechanics, revealing the surprising effects of quantum statistics on large systems. Experimental evidence supports the theory strongly. Landmark experiments include the measurement of gas pressure and temperature that confirmed Maxwell's velocity distribution, and observations of Brownian motion, which demonstrated the random motion of microscopic particles predicted by Einstein and Perrin. Observational confirmation of statistical mechanics extends to heat capacities of solids, conductivity of metals, and properties of liquids and gases under varying conditions. These experiments demonstrate that the statistical approach accurately predicts real-world behavior. The applications of statistical mechanics are vast. In technology, it underlies the design of engines, refrigerators, and air conditioners, and guides the development of new materials and nanotechnology. Its scientific importance lies in providing a fundamental explanation for thermodynamic laws and bridging classical and quantum physics. Understanding the statistical nature of matter allows scientists to predict outcomes in chemistry, biology, and even astrophysics, where large systems of particles interact over time. Statistical mechanics also carries deep conceptual and philosophical implications. It challenges the deterministic view of the universe by showing that macroscopic order arises from microscopic randomness. It impacts our understanding of reality, revealing that certainty in large systems is a result of probabilities rather than absolute rules. This framework encourages a shift in perspective, where chance and probability are as fundamental as cause and effect in describing nature. Modern developments in statistical mechanics continue to explore complex systems, non-equilibrium phenomena, and quantum information. Current research directions include understanding how systems evolve over time far from equilibrium, predicting behavior of strongly interacting particles, and applying concepts to biological and ecological networks. Open questions remain about the limits of predictability, emergence of complexity, and connections between information theory and physical laws. In summary, statistical mechanics provides a bridge between the tiny world of atoms and the large-scale behavior we observe. It allows us to understand heat, energy, and matter in a unified way, making predictions that align with experiments and guide technological innovation. Core takeaways are that randomness at the microscopic level leads to order at the macroscopic level, probability governs behavior, and energy and entropy are central to understanding natural processes. Looking ahead, statistical mechanics continues to expand our understanding of nature. By exploring the interplay of chance, energy, and matter, it reminds us that the universe is both predictable and surprising, and that deep insights can emerge from observing countless tiny particles working together to create the world we see. Nuclear shell model. The nuclear shell model is a way to understand how protons and neutrons are arranged inside the nucleus of an atom. Just like electrons are arranged in shells around the nucleus, nucleons, which include protons and neutrons, are thought to occupy different energy levels or shells within the nucleus. This model helps explain why some nuclei are especially stable while others are more likely to undergo radioactive decay. In everyday life, the nuclear shell model connects to how elements behave, how nuclear energy is produced, and why certain isotopes are used in medicine or power generation. Understanding the structure of the nucleus is important for everything from nuclear reactors to medical imaging and even predicting the stability of elements in the periodic table. The idea of the nuclear shell model emerged in the mid-20th century. Scientists were trying to make sense of why some nuclei were more stable than others. Observations showed that nuclei with certain numbers of protons or neutrons were unusually stable, a phenomenon later called magic numbers. This prompted researchers to develop a new theory that could explain these patterns. The origin of the theory can be traced back to 1949, when Maria Goeppert-Mayer and J. Hans D. Jensen independently proposed the concept of nucleons filling shells within the nucleus, similar to electron shells. Both scientists received the Nobel Prize in Physics in 1963 for this work. Their contributions were crucial in advancing our understanding of nuclear structure. Before the shell model, scientists primarily relied on the liquid drop model, which treated the nucleus like a droplet of incompressible fluid. This model could explain some aspects of nuclear behavior, such as binding energy trends and fission, but it could not account for the stability of nuclei with magic numbers. The core problem was that certain nuclei were far more stable than the liquid drop model predicted. A new framework was needed to explain these exceptions and to provide a more accurate picture of nuclear structure. The nuclear shell model is built on a few fundamental principles. The central postulate is that nucleons move in quantized energy levels or shells inside the nucleus. These shells are filled according to the Pauli exclusion principle, which states that no two nucleons can occupy the same quantum state. Key assumptions include that each nucleon moves independently in an average potential created by all other nucleons and that interactions between nucleons are secondary to the main shell structure. The mathematical and conceptual framework of the shell model uses quantum mechanics. Nucleons are described by wave functions and quantum numbers, similar to electrons in atoms. Core equations involve the Schrödinger equation, which helps calculate energy levels within the nucleus. Essential concepts include energy levels, spin-orbit coupling, and magic numbers, which are specific numbers of protons or neutrons that lead to extra stability. These ideas allow scientists to predict nuclear properties, such as magnetic moments, spin, and excited states of nuclei. The nuclear shell model predicts several key phenomena. One major consequence is the explanation of magic numbers, which are 2, 8, 20, 28, 50, 82, and 126. Nuclei with these numbers of protons or neutrons are highly stable and less likely to undergo decay. Another unique behavior explained by the model is the presence of nuclear spin and parity, which are properties that describe the orientation and symmetry of the nucleus. The model also accounts for energy gaps between shells, which influence the likelihood of nucleons jumping to higher energy levels. Experimental evidence for the nuclear shell model came from observations of nuclear spins, magnetic moments, and patterns of nuclear stability. Landmark experiments included the study of isotopes with magic numbers, where scientists noticed sudden jumps in binding energy and changes in nuclear behavior. Observational confirmation also came from spectroscopy of nuclei, which showed discrete energy levels consistent with the predicted shell structure. These findings provided strong support for the theory and its assumptions. The applications and impact of the nuclear shell model are wide-ranging. Technologically, it helps in designing nuclear reactors, managing radioactive isotopes, and developing medical imaging techniques using nuclear properties. Scientifically, it is important because it provides a framework for understanding the stability of elements, predicting nuclear reactions, and guiding research in nuclear physics and chemistry. The conceptual and philosophical implications of the nuclear shell model are profound. It changed our understanding of the nucleus from a simple uniform mass to a complex, structured system with order and predictability. This shift demonstrates how patterns and rules exist even in the smallest components of matter. The model encourages a deeper reflection on how fundamental laws of physics shape the material world and influence technological progress. Modern developments in the nuclear shell model focus on refining the model to include more complex interactions between nucleons and the effects of nuclear deformation. Current research explores exotic nuclei far from stability, neutron-rich isotopes, and the behavior of superheavy elements. Open questions remain about how nucleons interact at extreme energies and densities, and how the model can be unified with other aspects of nuclear theory, such as collective motion and nuclear forces. In summary, the nuclear shell model is a cornerstone of nuclear physics. It explains why some nuclei are exceptionally stable, predicts properties like spin and energy levels, and provides a framework for understanding nuclear behavior. The model connects abstract quantum mechanics to observable phenomena and practical applications, from energy production to medicine. Reflecting on the nuclear shell model, it is remarkable how a concept inspired by the arrangement of electrons can reveal hidden order in the heart of matter. The model reminds us that nature often follows elegant patterns, and even the tiniest particles are part of a structured, comprehensible universe. The journey of understanding the nucleus continues to inspire curiosity, innovation, and wonder in the world of science. Solid-state physics. Solid-state physics is the study of how atoms and electrons are arranged in solid materials and how these arrangements determine the properties of the material. Band theory is a key concept in this field, explaining how electrons move in solids and why some materials conduct electricity while others do not. Everyday objects, such as smartphones, computers, light bulbs, and solar panels, all rely on the principles of solid-state physics and band theory. These theories help us understand why metals shine and conduct, why insulators resist electric flow, and how semiconductors power modern electronics. The origin of band theory can be traced back to the early 20th century when scientists were trying to explain the electrical behavior of materials. Before this, classical physics could not explain why some materials conducted electricity while others did not. The need for a new approach arose because observations of metals and nonmetals showed patterns that defied simple laws of classical mechanics. Key scientists like Felix Bloch, Arnold Sommerfeld, and Neville Mott contributed to developing the framework. Bloch introduced the idea that electrons in a crystal move in a periodic potential, while Sommerfeld extended the free electron model to account for metals. Their work laid the foundation for understanding electronic bands in solids. The core problem that band theory addresses is understanding how electrons behave in solids. Earlier models treated electrons as free particles or as being attached to individual atoms. These models could not explain phenomena such as electrical conductivity in metals, the insulating nature of diamond, or the semiconducting properties of silicon. A new framework was needed to describe the collective behavior of electrons in a crystal lattice and to predict the energy levels that electrons could occupy. Band theory rests on several fundamental principles. The central postulate is that the electrons in a solid experience a periodic potential due to the repeating arrangement of atoms. This periodicity creates allowed and forbidden energy ranges called bands and band gaps. Another key assumption is that electrons obey quantum mechanics and the Pauli exclusion principle, meaning no two electrons can occupy the same quantum state simultaneously. Together, these principles explain why some solids conduct electricity and others do not. The mathematical and conceptual framework of band theory involves treating electrons as waves moving through a crystal lattice. Core equations include the Schrödinger equation applied to periodic potentials. Solutions to these equations produce energy bands where electrons can exist and band gaps where they cannot. Essential concepts include the valence band, which contains electrons bound to atoms, and the conduction band, where electrons can move freely to carry current. The size of the band gap determines whether a material is a conductor, semiconductor, or insulator. Band theory predicts several key phenomena. It explains the differences in electrical conductivity between metals, semiconductors, and insulators. In metals, the valence and conduction bands overlap, allowing electrons to move freely. In insulators, the band gap is wide, preventing electron flow. Semiconductors have moderate band gaps that can be bridged by adding energy, enabling controlled conduction. Unique behaviors explained by band theory include superconductivity at low temperatures and the photoelectric effect in semiconductors used in solar cells. Experimental evidence for band theory comes from several landmark studies. X-ray diffraction experiments confirmed the periodic arrangement of atoms in crystals, supporting the idea of a periodic potential. Electrical conductivity measurements and photoemission spectroscopy provided direct evidence of energy bands and band gaps. Observations such as the temperature dependence of conductivity in semiconductors and the behavior of metals under magnetic fields further confirmed the predictions of band theory. Applications of band theory are vast and technologically vital. Semiconductors form the basis of modern electronics, including transistors, diodes, and integrated circuits. Solar cells, LEDs, and lasers rely on the control of electron flow between bands. Scientific importance lies in the theory's ability to unify understanding of a wide range of solid materials and predict new behaviors, guiding the development of new materials with specific properties. Band theory also has conceptual and philosophical implications. It changes how we view matter at a fundamental level, showing that the behavior of electrons in solids is collective rather than individual. This shift helps us understand that material properties emerge from atomic arrangements and quantum rules rather than just the sum of individual atoms. It also challenges our intuition about electricity and conductivity, showing that quantum mechanics governs even everyday materials. Modern developments in solid-state physics continue to expand on band theory. Research focuses on topological insulators, graphene, and two-dimensional materials, where electrons exhibit unusual behaviors. Scientists are also exploring quantum computing and spintronics, which rely on manipulating electron states in novel ways. Open questions remain about high-temperature superconductivity and the full potential of engineered materials, keeping the field dynamic and evolving. In summary, band theory provides a framework to understand the electronic structure of solids. It explains why materials conduct or resist electricity, predicts their behavior under different conditions, and has wide-ranging applications in technology. The core takeaways are that electron behavior in solids is governed by quantum mechanics, periodic potentials create energy bands, and band gaps determine electrical properties. Reflecting on band theory, it becomes clear that our understanding of the physical world is deeply shaped by quantum principles. Everyday technologies like computers, phones, and solar cells rely on insights gained from this theory. Looking forward, continued research in solid-state physics promises to unlock new materials and devices, reshaping how we interact with and manipulate the world around us. String theory. Imagine a universe that is far more mysterious than the stars we see in the night sky. A universe where the tiniest building blocks of matter are not particles, but vibrating strings. String theory opens a door to understanding this hidden world and connects the smallest scales to the vast cosmos. The idea of strings began decades ago when scientists noticed that particles could behave like tiny loops or strands rather than point-like dots. In the 1960s, researchers studying the strong nuclear force stumbled upon mathematical patterns that suggested a new way to describe particles. Key scientists like Gabriele Veneziano, Leonard Susskind, and Michael Green helped shape the theory into what it is today. At its core, string theory proposes that all matter and forces come from one basic principle. The universe is made of extremely small strings that vibrate at different frequencies. Each vibration creates a different particle, similar to how different notes emerge from a guitar string. The central idea is that these strings are the fundamental units of reality, replacing the traditional point-like particles of physics. To understand how it works, imagine a framework where strings move through space and time, stretching, looping, and interacting. These strings can be closed loops or open strands, and their vibrations determine the mass and charge of particles. Extra dimensions beyond the familiar three of space and one of time are also part of the framework. These dimensions are hidden and compact, curled up so tightly that we cannot see them directly. Together, strings, their vibrations, and these extra dimensions create the fabric of reality. String theory attempts to explain problems that other theories struggle with. It addresses the nature of gravity at tiny scales, where classical physics fails. It also tries to unify quantum mechanics, which governs the very small, with general relativity, which governs the very large. Traditional models leave gaps when describing black holes, the early universe, or the behavior of particles at extremely high energies. String theory offers a potential bridge over these gaps. The predictions of string theory are profound, though mostly theoretical for now. It suggests the existence of multiple dimensions beyond the four we know. It predicts that every particle has a corresponding partner in its vibration spectrum. If proven, these predictions could transform our understanding of energy, matter, and the universe itself. Some consequences include new insights into black holes, the Big Bang, and even the possibility of parallel universes. String theory has several strengths that make physicists take it seriously. It unifies all fundamental forces under one framework. It offers consistent mathematical solutions where traditional physics runs into contradictions. Some calculations using string theory have matched known results in quantum field theory, showing that the theory has predictive power. It gives hope for a theory of everything, a single explanation for all natural phenomena. However, string theory also faces major challenges. It is extremely difficult to test experimentally because the strings are far too small to observe directly. Many of its predictions occur at energy levels beyond current technology. There are also open questions about which version of the theory correctly describes our universe. Critics argue that until experiments can confirm its predictions, string theory remains speculative. String theory connects deeply with other areas of physics. It builds on the principles of quantum mechanics, extending them into new dimensions. It also incorporates gravity naturally, something that quantum mechanics alone cannot do. Cosmologists use string theory ideas to model the early universe and black holes. This link between the very small and the very large makes it a unique bridge across physics. Today, research in string theory continues at universities and laboratories around the world. Scientists are exploring new mathematical tools, testing indirect predictions, and refining the theory to match observations. While it is not yet proven, string theory is widely respected for its potential to answer fundamental questions. Many physicists see it as a promising path toward a deeper understanding of the universe. String theory matters because it challenges our perception of reality. It impacts physics by offering a unified view of matter, energy, and forces. Beyond science, it inspires imagination, philosophy, and curiosity about our place in the cosmos. It encourages humans to think about dimensions beyond what we see and possibilities beyond what we can measure. In the end, string theory reminds us that the universe may be far more intricate than we can imagine. It asks us to consider reality as a symphony of tiny vibrating strings, where every note contributes to the cosmic melody. As research progresses, perhaps one day we will fully understand the music behind existence and discover the ultimate patterns that shape everything around us. M-theory. Mystery surrounds the idea of M-theory, one of the most fascinating concepts in modern physics. It is believed to be a theory that could explain the deepest secrets of the universe. Scientists think it could show how all forces and particles are connected, offering a glimpse into the very fabric of reality. The relevance of M-theory lies in its promise to unify our understanding of space, time, matter, and energy. It suggests that the universe may have more dimensions than we can see and that hidden structures govern the cosmos. The origins of M-theory can be traced back to the 1970s and 1980s when physicists were exploring string theory. String theory proposed that the basic building blocks of the universe are not point-like particles but tiny vibrating strings. However, string theory had multiple versions that seemed incompatible with each other. This puzzle led scientists to look for a more complete framework, which eventually became M-theory. Key scientists involved in its development include Edward Witten, who is often credited with unifying the different string theories, and Michael Duff, who contributed important mathematical insights. Their work transformed a collection of ideas into a potential single theory. The fundamental principle of M-theory is that all particles and forces arise from one underlying structure, often imagined as tiny multidimensional strings or membranes called branes. According to the theory, these strings vibrate at different frequencies, giving rise to the various particles we observe. The central mathematical idea is the existence of 11 dimensions, 7 more than the 3 dimensions of space and 1 of time that we experience. These extra dimensions are compactified or hidden, shaping the behavior of particles and forces in ways that are not yet fully observable. M-theory works by connecting different versions of string theory into one framework. In this basic framework, the universe is made up of tiny strings and higher-dimensional branes that interact in complex ways. Key components include open and closed strings, which can stretch and vibrate, and membranes, which can have multiple dimensions. The theory also introduces the concept of a multiverse, where multiple universes might exist in parallel, each with its own physical laws. These components together form a picture of a dynamic, intricate universe where everything is connected. One of the main goals of M-theory is to explain problems that remain unsolved in physics. It attempts to unify general relativity, which describes gravity and the large-scale structure of the universe, with quantum mechanics, which explains the behavior of the very small. By doing so, it addresses gaps in existing theories, such as the behavior of black holes and the nature of dark matter and dark energy. M-theory also seeks to answer why the fundamental constants of nature have the values they do and why the universe appears fine-tuned for life. The major predictions or implications of M-theory are profound. It suggests the existence of extra dimensions beyond what we can see and predicts that particles are manifestations of vibrating strings or membranes. The theoretical consequences include the possibility of a multiverse, new types of particles, and deeper insights into the origins of the cosmos. If confirmed, these predictions could revolutionize our understanding of reality and provide answers to questions that have puzzled scientists for centuries. M-theory has several strengths and achievements. One success is its ability to connect previously conflicting string theories into a single consistent framework. Physicists take it seriously because it provides a way to unify all fundamental forces, including gravity, electromagnetism, and nuclear forces. It also offers elegant mathematical structures that match observations in certain limits. These successes have made M-theory a central focus in theoretical physics, inspiring new research and mathematical discoveries. However, the theory also faces challenges and criticisms. Many problems remain unsolved, such as understanding the precise shape of extra dimensions and making predictions that can be tested experimentally. The energy scales required to probe these dimensions are far beyond current technology, making direct confirmation nearly impossible at present. Critics also argue that without experimental evidence, M-theory risks remaining a mathematical curiosity rather than a physical theory. Despite these challenges, research continues, driven by the hope that new ideas or technologies may one day provide proof. M-theory is deeply connected to other areas of physics. It builds on quantum mechanics by explaining particle behavior through string vibrations and incorporates gravity through its higher dimensional structure. This link provides a potential way to reconcile general relativity with quantum physics, a problem that has resisted solution for decades. It also connects to cosmology by offering explanations for the early universe, cosmic inflation, and the potential existence of multiple universes. Currently, M-theory is an active field of research. Physicists continue to explore its mathematical structure, search for indirect evidence, and develop new models. Its acceptance level is high among theoretical physicists as a promising framework, but it remains speculative because experimental confirmation is lacking. Universities and research institutions around the world study its implications, showing that the theory, though incomplete, has become a vital part of modern physics thinking. M-theory matters because it pushes the boundaries of human knowledge. It impacts physics by offering a potential unified theory of everything, providing insights into the fundamental workings of nature. Beyond physics, it inspires philosophical questions about the nature of reality, the possibility of other universes, and the limits of human understanding. Its broader significance lies in its ability to challenge our imagination and expand the scope of what we consider possible in the universe. In closing thought, M-theory invites reflection on the mysteries that surround existence. It reminds us that the universe is far more complex and interconnected than everyday experience suggests. The future outlook for M-theory holds both promise and uncertainty, with new mathematical developments and technological advances potentially unlocking its secrets. It encourages us to continue exploring, questioning, and seeking understanding, showing that the journey to uncover the ultimate truths of the universe is as fascinating as the answers themselves. Loop quantum gravity. The universe is full of mysteries. One of the greatest puzzles is understanding the very fabric of space and time. Scientists have long wondered what happens at the smallest scales of the cosmos, where the rules of classical physics no longer apply. Loop quantum gravity is a theory that attempts to answer these questions. It aims to uncover the hidden structure of space and time and shows why the universe behaves the way it does at its most fundamental level. This makes it highly relevant to understanding everything from black holes to the origins of the universe itself. The idea of loop quantum gravity has roots in the late 20th century. It began as scientists tried to unify general relativity, which describes gravity, with quantum mechanics, which governs the microscopic world. The theory emerged in the 1980s, inspired by the need to describe space and time as quantum objects rather than smooth, continuous backgrounds. Key figures in developing the theory include Carlo Rovelli, Lee Smolin, and Abhay Ashtekar, who helped shape the mathematical framework and introduced innovative concepts that brought the idea to life. At its core, loop quantum gravity is built on a simple but powerful principle. Space is not continuous. Instead, it is made up of tiny discrete loops, like a fine network of threads forming a fabric. These loops represent the smallest possible units of space. The central mathematical idea involves describing these loops using quantum geometry. Unlike ordinary geometry, where distances and areas can be measured continuously, quantum geometry measures them in discrete chunks. This concept changes how we think about space and time at the Planck scale, which is incredibly tiny, about a billionth of a billionth of a billionth of a meter. The framework of loop quantum gravity explains the structure of the universe through networks called spin networks. These networks are made up of nodes and links, which represent quantized volumes of space and their relationships. The nodes can be thought of as tiny chunks of space, while the links describe how they are connected. Space evolves over time in a way described by spin foams, which are like histories of spin networks moving and changing. This approach does not rely on a background space, meaning space itself emerges from the quantum properties of these loops. Loop quantum gravity tries to explain phenomena that standard theories cannot fully describe. It addresses the problem of singularities, such as those found at the centers of black holes or at the Big Bang, where conventional physics breaks down. The theory offers a way to avoid these infinities by showing that space is discrete at the smallest scales. It also fills gaps in existing theories, providing a bridge between quantum mechanics and gravity. Without such a theory, our understanding of the universe remains incomplete. The predictions of loop quantum gravity are both fascinating and profound. It suggests that space itself has an atomic structure, with smallest units that cannot be divided further. The theory predicts that black holes have quantized areas and volumes, which could explain their mysterious entropy and radiation properties. It also implies that the very early universe underwent a quantum phase, potentially smoothing out irregularities and shaping the cosmos as we see it today. These consequences challenge our classical view of reality and open the door to new ways of understanding time, space, and gravity. The theory has achieved notable successes. It provides a consistent mathematical framework that does not contradict known physical laws. Physicists take it seriously because it preserves the principles of quantum mechanics while addressing gravity in a novel way. Loop quantum gravity has produced meaningful insights into black hole physics, the Big Bang, and the nature of spacetime itself. These achievements make it a promising alternative to other approaches, such as string theory. Despite its successes, loop quantum gravity faces challenges. Many questions remain unanswered, including how the theory connects precisely with known particle physics. Experimental verification is extremely difficult because the effects occur at scales far smaller than we can currently observe. Direct tests of the theory are beyond the reach of existing technology, which makes it more of a mathematical and conceptual framework at this stage. These limitations do not diminish its importance but remind us of the work still needed to fully understand the universe. The theory also connects deeply with other areas of physics. It extends the principles of quantum mechanics to the structure of space itself, creating a bridge between two pillars of modern science. In relation to gravity and cosmology, loop quantum gravity offers explanations for cosmic phenomena that traditional theories struggle to describe. Its insights could ultimately reshape how we understand the evolution of the universe and the behavior of black holes. Research in loop quantum gravity is ongoing. Scientists continue to refine its mathematical framework and explore its implications. While it is not yet universally accepted, it is respected in the scientific community and remains an active field of study. The theory is gradually gaining support as its predictions and potential applications are examined more closely, keeping the hope alive that one day it could be confirmed by observation or experiment. The significance of loop quantum gravity extends beyond physics. It challenges our understanding of reality and inspires us to think differently about space, time, and existence. By uncovering the quantum structure of the universe, it changes how we see the cosmos and our place within it. Its broader significance lies in its ability to combine the known and the unknown, giving humanity a path toward deeper knowledge of the universe. Ultimately, loop quantum gravity invites reflection. It shows that the universe is far more intricate than we imagined, built from tiny loops that weave the fabric of reality. Philosophically, it reminds us that the world is both mysterious and understandable through the language of science. Looking ahead, the theory may continue to evolve, guiding future discoveries and reshaping our understanding of the cosmos in ways we cannot yet fully imagine. Supersymmetry. Mystery surrounds the universe in many ways. One of these mysteries is why the building blocks of nature behave the way they do. Supersymmetry is a theory that tries to uncover some of these secrets. It suggests that every particle we know has a hidden partner. This idea is fascinating because it could explain puzzles about the universe that we have not solved yet. It connects the very small world of particles to the large structure of the cosmos, making it deeply relevant to understanding everything around us. The idea of supersymmetry did not appear overnight. It emerged in the 1970s when physicists were searching for a way to unify different forces in nature. They noticed that the mathematical equations describing particles might work better if each particle had a partner with different spin properties. Some of the key scientists involved in this early work include Julius Wess and Bruno Zumino. Their contributions laid the foundation for what would become one of the most important concepts in theoretical physics. At its core, supersymmetry is built on a simple principle. For every known particle, there exists a corresponding particle called a superpartner. These superpartners differ in a property called spin. Particles like electrons, which are fermions, would have boson partners, and bosons, like photons, would have fermion partners. The central mathematical idea involves symmetry transformations that connect these two types of particles. This symmetry is not visible in our everyday experience, but it might be a hidden feature of the universe that helps maintain balance in nature. To understand how supersymmetry works, imagine a mirror for every particle. This mirror particle shares many properties with its original but differs in spin. The basic framework uses mathematical rules from quantum mechanics and field theory to predict the existence of these superpartners. The key components of supersymmetry include particles like selectrons, which mirror electrons, and squarks, which mirror quarks. These particles are not yet observed, but they are predicted to exist under the theory. Supersymmetry tries to answer some big questions. It addresses problems such as why gravity is so much weaker than other forces, why the Higgs boson is lighter than expected, and what dark matter could be made of. These gaps exist in current theories, like the Standard Model, which explains many particles and forces but cannot answer every mystery of the cosmos. Supersymmetry could fill these gaps and provide a more complete picture of reality. The theory also makes major predictions. If supersymmetry is correct, new particles should exist at energy levels just beyond what we have currently observed. These superpartners could be detected in high-energy experiments, such as those conducted at the Large Hadron Collider. The theoretical consequences include a more stable universe and explanations for phenomena that otherwise remain mysterious. Supersymmetry could also unify forces in ways that deepen our understanding of nature. Physicists take supersymmetry seriously because it has strengths and achievements. It has helped solve mathematical problems in quantum theory and has guided experiments in particle physics. Even though superpartners have not been directly observed, the theory provides logical consistency and elegant solutions to complex problems. Its success lies in offering new paths for understanding the fundamental rules of nature, which makes it a promising field of research. However, challenges and criticisms remain. One open problem is that superpartner particles have not yet been detected, despite many experiments. This raises questions about whether supersymmetry exists in the form originally predicted. Experimental limitations, such as the need for higher energy levels and more sensitive detectors, have slowed progress. Physicists continue to test the theory carefully, knowing that its confirmation would require precise and challenging measurements. Supersymmetry is closely connected to other theories in physics. It links naturally with quantum mechanics, which governs the behavior of very small particles. It also connects with gravity and cosmology, providing ideas about how the universe evolved and what dark matter might be. These links show that supersymmetry is not isolated but is part of a larger framework attempting to explain everything from the tiniest particle to the largest galaxy. Currently, supersymmetry remains an active area of research. Experiments continue to search for superpartners, and theoretical work explores new versions of the theory. Its acceptance level is cautious but hopeful. Many physicists believe that even if the original form of supersymmetry is not found, its concepts may guide future discoveries and innovations in particle physics. Supersymmetry matters because it could transform our understanding of the universe. It impacts physics by offering solutions to unanswered questions and by guiding experimental research. Beyond science, it has broader significance, reminding us that the universe may have hidden layers and unseen connections. It encourages curiosity and the belief that reality is richer than what we can immediately observe. In closing, supersymmetry invites both wonder and reflection. It challenges our perception of reality and asks us to consider that for every particle we know, a hidden counterpart may exist. The future of supersymmetry may reveal secrets that change our understanding of the cosmos, showing that the universe is even more intricate and beautiful than we can imagine. Grand Unified Theory. The Grand Unified Theory is a concept in physics that aims to explain all the fundamental forces of nature under a single framework. It is the idea that the different forces we see in the universe, such as electromagnetism, the strong nuclear force, and the weak nuclear force, may all be manifestations of one basic force. Scientists are motivated by the search for simplicity and understanding because the universe seems to follow certain rules that can be expressed mathematically. By unifying these forces, physicists hope to reveal a deeper order in nature and better understand the origin and behavior of the cosmos. The relevance of the Grand Unified Theory to the universe is profound. If successful, it would allow us to explain why particles behave the way they do, why the universe evolved as it did, and potentially unlock insights into the earliest moments after the Big Bang. It could provide a complete map of the laws that govern matter and energy, bridging gaps in our knowledge and connecting phenomena that now seem separate. The idea of a grand unified theory originated in the 1970s when physicists began to notice similarities between different forces. Scientists like Sheldon Glashow, Abdus Salam, and Steven Weinberg were among the key figures who worked on unifying electromagnetism with the weak nuclear force. They laid the groundwork for what became known as the electroweak theory, which demonstrated that at high energies, these two forces are actually part of the same force. This historical development set the stage for further attempts to include the strong nuclear force in a unified framework, pushing physics toward a more complete theory of everything. At its core, the Grand Unified Theory is based on a fundamental principle, that the laws of physics are unified and consistent at the most basic level. It suggests that the different forces are not separate, but instead emerge from a single underlying symmetry. The central mathematical idea involves complex equations from quantum field theory and group theory, which describe how particles interact through these forces. These equations aim to show that at extremely high energies, the distinctions between forces disappear, revealing a simpler and more elegant structure of nature. The way the Grand Unified Theory works is through a framework that combines the standard model of particle physics with new concepts that extend beyond it. It focuses on key components such as quarks, leptons, gauge bosons, and the symmetries that connect them. By exploring how these particles behave at very high energies, physicists can test the predictions of the theory and determine whether the forces truly merge under extreme conditions, like those present just after the Big Bang. The Grand Unified Theory tries to explain several problems in physics. It addresses questions about why forces have different strengths, why particles have the masses they do, and why the universe has the structure we observe today. It also aims to fill gaps in existing theories, such as the inability of the Standard Model to explain gravity or the matter-antimatter imbalance in the universe. By providing a unifying framework, it seeks to answer questions that have puzzled scientists for decades. One of the major predictions of the Grand Unified Theory is proton decay, which suggests that even protons, thought to be stable, could break down over incredibly long timescales. The theory also predicts relationships between particle masses and the strength of forces at high energies. The theoretical consequences are profound, potentially leading to new understanding of the early universe, the behavior of black holes, and even the ultimate fate of matter in the cosmos. The strengths and achievements of the Grand Unified Theory include its ability to simplify our understanding of nature. The unification of the electromagnetic and weak forces into the electroweak theory has been experimentally confirmed, showing that such unification is possible. Physicists take the theory seriously because it provides a coherent framework that could one day connect all fundamental forces, moving closer to a theory of everything. However, the theory also faces challenges and criticisms. Many predictions, such as proton decay, have not yet been observed, leaving open problems. Experiments are limited by the extreme energies needed to test the theory directly, far beyond what current particle accelerators can achieve. These challenges remind us that the path to understanding the universe is difficult and that nature may be more complex than our current models suggest. The Grand Unified Theory connects with other theories in physics. It links with quantum mechanics because it describes the behavior of particles at very small scales, and it interacts with theories of gravity and cosmology when trying to include the force of gravity in a unified framework. These connections hint at the possibility of an even broader theory that encompasses all physical phenomena, including space, time, and matter. Currently, research into the Grand Unified Theory is ongoing. Physicists continue to refine models, conduct experiments in particle accelerators, and search for rare events like proton decay. While the theory is not yet confirmed, it is widely respected and remains a central goal of theoretical physics. The present acceptance level is cautious optimism, with many scientists believing that a full unification is possible, even if it may take decades to achieve. The significance of the Grand Unified Theory is immense. It could revolutionize physics by providing a single framework for understanding all forces and particles. Beyond physics, it carries philosophical weight, suggesting that the universe is governed by elegant and simple laws. Understanding these laws could change our view of reality, our place in the cosmos, and our conception of nature itself. In closing thought, the Grand Unified Theory reflects humanity's desire to seek unity in complexity. It is a reminder that the universe, despite its apparent chaos, may follow a deep and beautiful order. The future of this theory holds promise not only for science but also for our understanding of existence, inspiring wonder and curiosity about the hidden structure of reality and the ultimate nature of the universe. Higgs Mechanism. The Higgs mechanism is a fundamental concept in particle physics that explains how certain particles acquire mass. In the world of tiny particles, mass is not simply an inherent property but arises from interactions with a field that exists throughout the universe. This field, called the Higgs field, permeates all of space, and particles gain mass by interacting with it. Without the Higgs mechanism, particles like electrons would remain massless, and the universe as we know it, with atoms, planets, and life, could not exist. It is central to our understanding of why matter forms structures rather than dispersing as energy alone. The idea of the Higgs mechanism emerged from the need to resolve a puzzle in physics. During the mid-20th century, scientists were developing theories to explain the behavior of fundamental forces. They discovered that a theory describing the electromagnetic and weak nuclear forces worked beautifully, but only if particles had mass. Mass, however, seemed to break the mathematical consistency of the theory. This led to the search for a mechanism that could give mass without destroying the delicate structure of the theory. The concept was first introduced in the 1960s, with multiple scientists proposing similar ideas at the same time. Among the key contributors were Peter Higgs, François Englert, and Robert Brout, whose work laid the foundation for what would later be confirmed by experiments. At its core, the Higgs mechanism relies on a simple yet profound principle. It suggests that a field exists everywhere, even in empty space, and particles acquire mass through their interaction with this field. Some particles interact strongly and become heavy, while others interact weakly and remain light. The central physical idea involves spontaneous symmetry breaking, where the field chooses a specific configuration that makes mass possible while preserving the overall structure of the laws of physics. Mathematically, this is described by a field that has a non-zero value in its lowest energy state, leading to the emergence of a new particle known as the Higgs boson. The way the Higgs mechanism works can be visualized with the field and its interactions. Imagine the universe filled with a kind of invisible medium. As particles move through it, they experience resistance, which we perceive as mass. This framework requires the Higgs field itself and the Higgs boson, the particle associated with vibrations in the field. The discovery of the Higgs boson in 2012 at the Large Hadron Collider provided strong evidence that this mechanism truly exists. Key components include the different elementary particles such as quarks, electrons, and W and Z bosons, each interacting differently with the field to acquire mass. The Higgs mechanism attempts to explain why particles have mass in the first place. Without it, fundamental particles would remain massless, and atoms could not form. It addresses the problem of uniting the theory of forces with the existence of massive particles. Before the Higgs idea, the standard model of particle physics could not explain why the weak force carriers, the W and Z bosons, have mass while the photon does not. The mechanism fills this gap, providing a coherent explanation for the observed differences in particle masses and maintaining the consistency of the theory. The major predictions of the Higgs mechanism include the existence of a particle with certain properties, the Higgs boson, and the relationship between particle masses and their interaction strength with the field. It predicts that some particles should be heavy, others light, and that the Higgs boson should have a measurable mass itself. The theoretical consequences extend to the standard model of particle physics, confirming its structure and providing a foundation for understanding the forces that govern the universe at the smallest scales. The achievements of the Higgs mechanism are significant. Its success in explaining mass makes it a cornerstone of modern physics. The prediction and eventual discovery of the Higgs boson gave physicists confidence that the underlying principles are correct. It explains why the universe has structure and why matter can exist in the forms we observe. Physicists take it seriously because it resolves fundamental inconsistencies in theoretical models and connects abstract mathematics with observable reality. Despite its success, the Higgs mechanism faces challenges. Open problems include understanding why the Higgs boson has the mass it does and whether there are additional Higgs-like particles. Experimental limitations mean that studying the Higgs boson requires high-energy collisions in particle accelerators, making observations difficult and rare. Some aspects, like the exact nature of the field and its role in early universe cosmology, remain areas of active investigation. The Higgs mechanism connects deeply with other theories in physics. It is rooted in quantum mechanics, relying on fields, particles, and the principles of symmetry breaking. It also has implications for cosmology, such as the evolution of the early universe, inflation, and the stability of matter. While it does not directly explain gravity, its connection to the mass of particles indirectly links it to the curvature of space and the structure of the cosmos. Currently, research continues to probe the Higgs field and its interactions. Scientists at large facilities like CERN study its properties, looking for subtle deviations from predictions that could point to new physics. The Higgs mechanism is widely accepted within the scientific community as a valid explanation for particle mass, though questions remain that could lead to deeper understanding in the future. The significance of the Higgs mechanism goes beyond physics. It changes our view of the universe, showing that even empty space is filled with structure that shapes reality. Its discovery impacts technology, philosophy, and our understanding of existence. It reminds us that the universe is governed by hidden principles that can be uncovered through careful thought and experiment. The Higgs mechanism invites reflection on the nature of reality. It shows that the universe is not as simple as it appears and that even emptiness has meaning. The future may reveal more about how this field interacts with dark matter or other unknown phenomena, continuing the journey of discovery that began with a simple question about mass. Its story is a testament to human curiosity and the power of science to uncover the invisible forces shaping the cosmos. Quantum field theory in curved spacetime. Quantum field theory in curved spacetime is the study of how quantum fields behave in a universe where space and time are not flat but curved by gravity. It is a combination of quantum physics, which explains the behavior of very small particles, and general relativity, which explains gravity and the shape of the universe. This theory helps us understand how particles, energy, and forces interact in environments like near black holes or the expanding universe. It is important because it gives us insight into phenomena that occur on the largest and smallest scales of the cosmos, linking the quantum world with the shape of space and time. The idea of combining quantum theory with curved spacetime began in the early 20th century when scientists realized that the laws of quantum mechanics must work even in the presence of gravity. Albert Einstein's theory of general relativity described gravity as the bending of spacetime, while quantum mechanics described particles and fields. The origin of this idea came from trying to explain phenomena where both quantum effects and strong gravitational effects occur, such as near black holes. Key scientists involved include Stephen Hawking, who studied black hole radiation, and Robert Wald, who helped formalize the theory mathematically. Others like Paul Dirac and Bryce DeWitt also contributed important insights into how quantum fields respond to curved geometry. The fundamental principle of quantum field theory in curved spacetime is that fields and particles exist in a universe shaped by gravity. Unlike in flat space, the curvature affects how particles appear and how energy behaves. The central mathematical idea involves using the language of fields, which are quantities defined at every point in spacetime, and applying them to curved backgrounds. This involves complex equations that extend standard quantum field theory to include gravitational effects. The basic framework treats spacetime as a curved stage and quantum fields as actors moving on that stage. Fields like the electromagnetic field or scalar fields are analyzed in a way that accounts for the curvature of spacetime. Key components include the spacetime metric, which describes the shape of spacetime, quantum fields, and operators that measure quantities like energy or particle number. This framework allows physicists to study particle creation in the early universe or near black holes, where gravity is strong. Quantum field theory in curved spacetime tries to explain phenomena that ordinary quantum mechanics or general relativity cannot describe alone. It addresses problems like black hole radiation, the creation of particles from vacuum in an expanding universe, and the behavior of quantum fields under extreme gravitational conditions. It also fills gaps in existing theories by providing predictions where both gravity and quantum effects are important, areas where traditional physics often fails. Major predictions include the Hawking radiation from black holes, which suggests black holes can slowly lose mass and energy by emitting particles. Another prediction is the generation of particles in the early universe, contributing to the structure and evolution of the cosmos. The theoretical consequences include a deeper understanding of the relationship between energy, spacetime, and quantum mechanics, suggesting that even empty space can have complex quantum effects influenced by gravity. The theory has many strengths and achievements. It has successfully explained phenomena like black hole radiation and particle creation in expanding universes, which were previously mysterious. Physicists take it seriously because it has consistent mathematical foundations and leads to predictions that, at least in principle, can be tested. It also provides a bridge between quantum mechanics and general relativity, offering a step toward a unified theory of physics. However, there are challenges and criticisms. Open problems include the difficulty of fully quantizing gravity and understanding the deep connection between spacetime geometry and quantum fields. Experimental limitations make it hard to observe many predicted effects directly, because they often occur in extreme environments that are not easily accessible. Despite these challenges, the theory remains a central tool in theoretical physics. Quantum field theory in curved spacetime connects strongly with other theories. It extends quantum mechanics into curved spacetime, showing how particle behavior changes with gravity. It also links with gravity and cosmology, helping to explain black holes, the early universe, and the evolution of cosmic structures. These connections make it a key part of modern physics, uniting different areas under one framework. Currently, research is ongoing to better understand phenomena like quantum effects near black holes and in the early universe. Scientists continue to refine the mathematical tools and search for ways to test predictions through observations or experiments. The theory is well accepted in the physics community as a valid framework, though it is recognized as incomplete until a full theory of quantum gravity is achieved. Quantum field theory in curved spacetime matters because it impacts both physics and our understanding of the universe. It has led to important insights about black holes, the birth of the universe, and the nature of space and time. Beyond physics, it inspires philosophical reflection on the nature of reality, the role of observation, and the limits of human understanding. The theory suggests a universe that is far more dynamic and interconnected than previously imagined. Looking ahead, the future of this theory involves exploring quantum gravity and understanding how the smallest scales of nature connect with the largest. It challenges us to think about the universe in new ways, reminding us that even empty space has mysteries, and that the quantum world and the cosmos are deeply intertwined. Twistor Theory. Twistor theory is a mathematical framework developed to study the nature of space, time, and fundamental particles in the universe. It provides an alternative way of looking at physics by connecting geometry and quantum mechanics, allowing complex problems about the structure of the universe to be approached in a new and elegant way. This theory suggests that the basic building blocks of the universe might not be points in space and time, but rather more abstract objects called twistors that encode information about light rays and the fabric of spacetime itself. Its relevance lies in the possibility of bridging the gap between the physics of the very large, like stars and galaxies, and the very small, like electrons and quarks, helping scientists understand the universe more deeply. Twistor theory began as a bold idea in the late 1960s, proposed by the British mathematician Roger Penrose. Penrose was inspired by the challenge of unifying Einstein's theory of general relativity with the principles of quantum mechanics. The origin of the idea came from examining light and the way it moves through space. Penrose realized that by focusing on the paths of light rays rather than points in space, a new mathematical framework could be developed that simplifies some of the deepest problems in physics. Other key scientists who contributed include Michael Atiyah and Edward Witten, who expanded the theory and explored its connections to string theory and quantum field theory. The core concept of twistor theory revolves around a simple but profound principle. Instead of using ordinary coordinates to describe points in spacetime, twistors use mathematical objects that encode information about light rays. These objects allow complex interactions between particles and fields to be represented more neatly, often reducing difficult equations into simpler forms. The central mathematical idea is that spacetime can be transformed into a twistor space, where geometric relationships are easier to see and manipulate. In this way, problems that are almost impossible in normal spacetime become more tractable. Twistor theory works by creating a bridge between standard spacetime and a new, abstract space called twistor space. The basic framework involves translating points and events in spacetime into twistors, which are complex numbers that encode direction and position of light rays. Key components include the twistor itself, which can represent a particle or photon, and the operations that combine twistors to describe interactions. By using these components, physicists can study phenomena such as particle scattering and gravitational fields with a new set of tools that often reveal hidden symmetries and patterns. The theory tries to explain problems that remain difficult in traditional physics. It addresses issues like the reconciliation of quantum mechanics with gravity, where current theories fail to fully agree. Twistor theory also fills gaps in existing models by offering alternative ways to describe fundamental interactions, especially where spacetime appears curved or behaves in unusual ways. It provides insights into the structure of space at very small scales, where ordinary geometric ideas break down. Twistor theory leads to major predictions and implications for physics. One expected outcome is a better understanding of particle interactions, particularly in quantum field theory. Theoretical consequences include simpler calculations of particle collisions, predictions of scattering amplitudes, and potential hints about quantum gravity. Although many predictions are still being tested, the mathematical structure of the theory itself has led to new ways of thinking about spacetime and quantum fields that are widely regarded as promising. The strengths and achievements of twistor theory are notable. Its successes include providing elegant solutions to previously unsolvable mathematical problems, influencing the development of string theory, and guiding research in quantum field theory. Physicists take it seriously because it offers concrete tools for understanding complex physical phenomena and because it reveals unexpected connections between geometry and fundamental forces. Its mathematical beauty and consistency give it a credibility that extends beyond its immediate predictions. Despite its promise, twistor theory faces challenges and criticisms. Open problems include fully connecting it with experimental data, and showing how it can completely unify gravity with quantum mechanics. Experimental limitations are significant because many of its predictions occur at energy scales that are not yet reachable in laboratories. As a result, much of the theory remains theoretical, requiring indirect evidence and mathematical consistency rather than direct experimental confirmation. Twistor theory connects with other areas of physics in profound ways. It links with quantum mechanics by offering new ways to calculate particle interactions and by providing insights into the probabilistic nature of quantum events. It also connects with gravity and cosmology by suggesting alternative descriptions of curved spacetime and black hole dynamics. These connections make twistor theory a bridge between disciplines that are often treated separately, showing the deep unity underlying physical laws. Currently, twistor theory is an active field of research. Scientists continue to explore its applications in quantum field theory, string theory, and the mathematics of spacetime. Its present acceptance is limited to specialized areas of theoretical physics, but it is regarded as a promising and serious framework. Researchers are investigating whether it can offer practical tools for calculating physical phenomena and whether it can inspire a more complete theory of the universe. Twistor theory matters because it impacts the way we understand the universe. Its ideas could eventually lead to breakthroughs in quantum gravity, particle physics, and cosmology. Beyond physics, it has broader significance by showing how abstract mathematics can reveal deep truths about reality, encouraging a more imaginative and conceptual approach to science. In closing, Twistor theory offers a philosophical reflection on the nature of reality. It suggests that the universe may be best understood not as points and distances, but as patterns of light and information. The future outlook is bright, as researchers continue to uncover connections and applications that may redefine our understanding of space, time, and the fundamental laws that govern existence. Holographic Principle. The holographic principle is a fascinating concept in modern physics that suggests the information contained within a volume of space can be represented as a theory that exists only on the boundary of that space. In other words, the universe might work like a hologram, where a two-dimensional surface encodes everything inside a three-dimensional space. This principle challenges our usual ideas about reality and space, offering a unique way to understand the universe at its most fundamental level. It is relevant because it connects gravity, quantum mechanics, and the structure of the cosmos, potentially offering answers to some of the deepest questions about the universe, such as the nature of black holes and the origin of spacetime itself. The idea of the holographic principle originated in the 1990s when physicists were trying to resolve contradictions between quantum mechanics and Einstein's theory of general relativity. The concept grew out of studies of black holes, where it was observed that the maximum amount of information inside a black hole is proportional not to its volume but to its surface area. Key scientists involved in developing this idea include Gerard T. Hooft, who first proposed the concept, and Leonard Susskind, who refined it and provided important theoretical support. Their work laid the foundation for thinking about the universe in a completely new way. At the core of the holographic principle is the fundamental idea that the information describing a three-dimensional space can be stored on a two-dimensional surface surrounding it. This principle suggests that our perception of depth and volume might emerge from information encoded elsewhere. The central mathematical concept involves entropy, a measure of information, and its relationship to surface area, rather than volume. In black hole physics, this is expressed through the Bekenstein-Hawking formula, which links the entropy of a black hole to the area of its event horizon. The way the holographic principle works can be understood by imagining a region of space and its surrounding boundary. According to the principle, all the information inside the region can be thought of as encoded on that boundary surface, like a three-dimensional image projected from a flat two-dimensional screen. The basic framework relies on concepts from quantum field theory and string theory. Key components include the bulk, which is the three-dimensional space inside, and the boundary, the two-dimensional surface that encodes the information. This approach offers a new way to unify gravity with quantum mechanics, which has been a major challenge in physics for decades. The principle tries to explain several deep problems in modern physics. It addresses the black hole information paradox, which questions what happens to information that falls into a black hole. Traditional theories suggested information could be lost, violating the laws of quantum mechanics, but the holographic principle proposes that the information is preserved on the black hole's surface. It also fills gaps in existing theories by offering a framework to understand how gravity and quantum mechanics can coexist and how spacetime might emerge from more fundamental information structures. Major predictions or implications of the holographic principle include the idea that the universe itself could be holographic. If true, this suggests that all physical phenomena, including matter, energy, and forces, might be encoded on a distant boundary or horizon. Theoretical consequences extend to cosmology, particle physics, and black hole physics. For instance, It could explain why the universe seems to have a finite amount of information and why the laws of physics appear consistent across vast distances. The strengths and achievements of this principle are significant. It has provided powerful tools for theoretical physics, particularly in understanding black holes and quantum gravity. Successes include the derivation of properties of black holes using holographic methods and connections to string theory that allow predictions about quantum systems. Physicists take it seriously because it provides a consistent way to reconcile gravity with quantum mechanics, a problem that has persisted for nearly a century. Despite its promise, the holographic principle faces challenges and criticisms. Open problems include the difficulty of testing the principle experimentally, as the boundaries it refers to may be beyond our observational reach. Experimental limitations make it hard to verify predictions directly, and some scientists argue that while it is mathematically elegant, its physical reality remains uncertain. Researchers continue to explore ways to test its consequences indirectly through cosmic observations or simulations of quantum systems. The principle connects deeply with other theories. It has strong links with quantum mechanics because it deals with information and entropy, central ideas in quantum theory. It also relates to gravity and cosmology, as it emerged from the study of black holes and offers insights into the structure of spacetime and the expansion of the universe. This connection makes it a promising bridge between two areas of physics that are otherwise difficult to unify. Currently, research on the holographic principle is active and ongoing. Scientists are exploring applications in quantum computing, cosmology, and theoretical physics. Its acceptance level varies. While widely respected in the theoretical physics community, it remains a hypothesis awaiting experimental confirmation. Many researchers consider it a guiding idea for new physics, while others approach it cautiously, aware of the gaps between theory and observation. The holographic principle matters because it challenges our understanding of reality itself. Its impact on physics could be profound, offering a path to unify fundamental forces and explaining deep cosmic mysteries. Beyond science, it has broader significance, inspiring philosophical reflections on the nature of existence and reality. If the universe is a hologram, the way we perceive space, matter, and time may be a projection of deeper informational structures that we are only beginning to glimpse. Reflecting on the holographic principle invites both wonder and humility. It reminds us that reality might be far stranger than our senses suggest and that the universe may be encoded in ways we are just starting to understand. Looking forward, research in this area could transform physics and our worldview, opening new paths to explore the ultimate structure of the cosmos and our place within it. Hawking radiation. Imagine a black hole, a cosmic object so dense that not even light can escape its grip. For decades, scientists believed black holes were completely dark, swallowing everything that came near. But in 1974, a groundbreaking idea changed that view forever. Stephen Hawking suggested that black holes are not entirely black. Instead, they slowly emit radiation, now known as Hawking radiation. This discovery bridges the worlds of quantum mechanics and general relativity, helping us understand the universe at its most extreme. It matters because it challenges our understanding of black holes and raises questions about the ultimate fate of matter and energy in the cosmos. Hawking radiation is the emission of particles from a black hole due to quantum effects near its event horizon. At its core, it reveals that black holes are not completely isolated but interact with the vacuum of space. The basic principle involves quantum fluctuations, where pairs of particles and antiparticles spontaneously appear and disappear. If one particle falls into the black hole while the other escapes, the black hole loses mass over time. The key components of this phenomenon include the event horizon, virtual particle pairs, and the energy balance that allows radiation to emerge. The idea of black holes emitting radiation has its roots in the study of quantum mechanics and general relativity. In the 1960s, physicists explored the behavior of particles near extreme gravitational fields. Stephen Hawking built on this work, combining quantum theory with Einstein's theory of general relativity. His calculations showed that black holes should emit thermal radiation, a surprising and revolutionary conclusion. This marked a milestone in theoretical physics, linking concepts that were once thought incompatible and earning Hawking a permanent place in the history of science. The process of Hawking radiation begins with the vacuum of space, where energy fluctuations constantly create virtual particle pairs. Near a black hole's event horizon, these pairs can become separated. One particle falls into the black hole, carrying negative energy relative to an outside observer, while the other escapes into space. The escaping particle appears as radiation, slowly reducing the black hole's mass. Mathematically, this process is described by the Hawking temperature formula, which relates the black hole's mass to the temperature of the emitted radiation. The smaller the black hole, the higher the temperature and the faster it radiates. The implications of Hawking radiation are profound. Physically, it suggests that black holes can evaporate over time, eventually disappearing entirely if they do not gain additional mass. This challenges the classical view of black holes as permanent objects. Observationally, detecting Hawking radiation is extremely difficult because the effect is incredibly weak for large black holes, but its theoretical existence has influenced the search for micro-black holes in particle accelerators and cosmic phenomena. Hawking radiation also connects to other areas of physics, including thermodynamics, quantum field theory, and the study of information loss in black holes. Despite its importance, Hawking radiation raises several challenges and questions. Measuring the radiation directly remains beyond current technology. Some scientists debate the implications for the conservation of information, leading to the famous information paradox. Questions about how quantum gravity fully integrates with Hawking's theory remain unresolved. Additionally, understanding the final stages of black hole evaporation requires a theory of quantum gravity that we do not yet possess. Modern research continues to explore these ideas. Scientists study analog systems, such as sonic black holes, to simulate Hawking radiation in laboratories. Theoretical work investigates the role of black holes in the early universe and in high-energy cosmic events. Researchers also consider the practical applications of understanding energy extraction from black holes and insights into fundamental physics. Future directions include refining the mathematics of quantum gravity, exploring possible connections to dark matter, and searching for indirect evidence of radiation in astrophysical observations. Hawking radiation also offers a philosophical perspective. It reminds us that the universe is full of hidden processes and that even the most powerful and mysterious objects are not beyond the laws of physics. It challenges our view of space, time, and energy, showing that the universe is dynamic and constantly changing. This radiation hints at a deeper unity between the quantum world and the cosmic scale, encouraging us to question what we know and to explore the unknown. In conclusion, Hawking radiation shows that black holes are not eternal prisons but dynamic objects slowly losing mass through quantum processes. From its theoretical origins to its profound implications for physics and philosophy, it continues to inspire curiosity and research. It reshapes our understanding of the universe, revealing the delicate interplay between gravity and quantum mechanics. The study of Hawking radiation invites us to imagine the universe as a place where even the darkest corners emit light, urging us to look deeper, question boldly, and seek answers to mysteries that lie at the edge of science. Inflationary Cosmology, Big Bang Inflation. The universe as we see it today is vast, filled with galaxies, stars, and planets. But if we imagine going back in time to the very beginning, everything was compressed into a tiny, dense point. Understanding how the universe expanded from that state has fascinated scientists for decades. Inflationary cosmology offers a compelling explanation for the rapid growth of the universe in its earliest moments. It helps us understand why the universe looks the way it does today and why certain patterns in space and matter exist. Exploring this topic allows us to connect the tiniest fractions of a second after the Big Bang to the enormous cosmos we observe now. At its core, inflationary cosmology is the study of how the universe expanded extremely rapidly just after the Big Bang. This concept builds on the idea that the universe did not grow slowly and steadily but underwent a period of exponential expansion. The key principle is that a tiny region of space grew faster than the speed of light in a fraction of a second. This rapid expansion smoothed out irregularities and set the stage for the formation of galaxies and cosmic structures. The main components of this theory include the inflation field, sometimes called the inflaton, and the energy driving this growth, which dominates the dynamics of the early universe. The idea of inflation began as scientists tried to solve problems in the original Big Bang model. Questions about why the universe appears uniform in all directions, or why there is no observed curvature, led researchers to look for an explanation. In 1980, physicist Alan Guth proposed the concept of inflation to address these issues. Soon after, André Linde and others refined the theory, introducing models that explained the mechanisms more precisely. Over the years, cosmologists have tested these ideas with observations of the cosmic microwave background and galaxy distributions, marking milestones that strengthened the theory and increased its acceptance in the scientific community. The process of inflation starts with the universe in a state of extremely high energy and density. During this period, the inflaton field drives a rapid expansion of space, increasing its size exponentially within a tiny fraction of a second. This expansion stretches tiny quantum fluctuations, which later become the seeds for galaxies and large-scale structures. As inflation ends, the energy stored in the inflaton field converts into matter and radiation, a process called reheating, which leads to the universe transitioning into the more familiar Big Bang expansion. The dynamics of this process can be described using equations from general relativity and quantum field theory, which help model the energy density, expansion rate, and fluctuation amplitudes. The implications of inflation are profound for our understanding of the universe. It explains why the universe appears nearly flat and uniform, and why distant regions share the same temperature despite never being in contact before inflation. Observational evidence supporting this theory comes from measurements of the cosmic microwave background, which reveal slight variations that match predictions from inflationary models. Inflation also connects to other areas of physics, such as particle theory and quantum mechanics, providing a framework for linking the behavior of the smallest particles to the structure of the entire cosmos. These connections make it a unifying concept in modern cosmology. Despite its successes, inflationary cosmology faces challenges. One limitation is that the exact nature of the inflaton field remains unknown. There are also debates about the initial conditions required for inflation and whether alternative models could explain the same observations. Some critics argue that the theory is difficult to test directly, relying on indirect evidence from cosmic background measurements. Unresolved questions include how inflation started, what triggers its end, and whether multiple inflationary periods could exist. Scientists continue to refine the models and search for observational signatures that could confirm or challenge the theory. Modern research in inflationary cosmology has explored new ways to test its predictions. Scientists study patterns in the cosmic microwave background with increasing precision, looking for signs of primordial gravitational waves that could confirm inflation. Theoretical work investigates connections between inflation and string theory or other high-energy physics models. Applications of this research are mostly theoretical but provide deep insights into the early universe and fundamental physics. Future directions include more precise measurements of cosmic radiation, galaxy surveys, and possibly new methods to detect effects from the universe's first moments. Philosophically, inflationary cosmology changes how we view the universe. It shows that the cosmos is not just vast but also dynamic, shaped by processes that occurred in an almost unimaginably short time. It highlights the connection between the smallest scales of quantum physics and the largest scales of cosmic structure. Inflation invites reflection on the origins and nature of reality, prompting questions about what existed before the universe expanded and how the laws of physics emerged. Understanding these ideas encourages curiosity and a sense of wonder about the universe's beginnings and its ongoing evolution. In conclusion, inflationary cosmology provides a powerful explanation for the universe's rapid early expansion and its current large-scale structure. It builds on the Big Bang model while addressing important questions about uniformity, flatness, and the seeds of galaxies. Key contributors like Alan Guth and Andre Linde laid the groundwork, and modern research continues to explore the details and consequences of inflation. While challenges and open questions remain, the theory connects deeply with fundamental physics and expands our understanding of the cosmos. Studying inflation encourages us to think about the universe in new ways, inspiring both scientific investigation and philosophical reflection about our place in this vast, expanding universe. Quantum gravity in cosmology. The universe has always fascinated humans, from the twinkling stars in the night sky to the vast, mysterious cosmos that stretches beyond our imagination. Among the most intriguing questions is how gravity works at the smallest and largest scales. Quantum gravity in cosmology seeks to answer this by combining the strange rules of quantum mechanics with the grand framework of Einstein's theory of relativity. Understanding this topic matters because it could explain the very beginning of the universe and the nature of black holes. It may reveal what happened in the first moments after the Big Bang, when the universe was unimaginably small and dense, and the usual laws of physics we know today were not enough. At its core, quantum gravity is the study of how gravity behaves according to the principles of quantum mechanics. Unlike classical gravity, which describes planets and stars moving in space, quantum gravity tries to understand gravity at the level of tiny particles and the fabric of spacetime itself. The basic idea is that space and time are not smooth and continuous but may have a granular structure at the smallest scales. Key components include the quantum fields, spacetime curvature, and fundamental particles like gravitons, which are hypothetical carriers of the gravitational force. The origins of this idea come from attempts to unify quantum mechanics with general relativity. While quantum mechanics governs the microscopic world and general relativity describes cosmic scales, combining them has been a challenge for over a century. Key contributors include Albert Einstein, whose theory of relativity redefined gravity, and modern physicists such as Stephen Hawking, Roger Penrose, and Carlo Rovelli, who explored black holes and loop quantum gravity. Milestones in the development include the formulation of quantum field theory, the discovery of Hawking radiation, and the proposal of string theory as a candidate for quantum gravity. Quantum gravity works by applying quantum principles to the structure of spacetime. At a step-by-step level, physicists begin with classical general relativity equations and then introduce quantum corrections. These corrections suggest that space and time may be made of tiny, discrete units. The dynamics of these units interact in ways that could smooth out singularities like the Big Bang or the center of black holes. Important equations include the Wheeler-DeWitt equation, which attempts to describe the quantum state of the universe, and modifications of Einstein's field equations to include quantum effects. The implications of quantum gravity are profound. Theoretically, it could resolve mysteries about black holes, cosmic inflation, and the true origin of the universe. Observational evidence is challenging to obtain, but scientists look for hints in cosmic microwave background radiation, gravitational waves, and black hole emissions. Quantum gravity also connects to other areas of physics, such as particle physics, cosmology, and string theory, creating a bridge between the very small and the very large. Despite its promise, quantum gravity faces several challenges. Current limitations include the lack of experimental confirmation and the difficulty of testing predictions at energies beyond our current technology. There are controversies and debates over competing theories, such as string theory and loop quantum gravity, with no consensus on which approach is correct. Many problems remain unresolved, including the precise nature of spacetime at the Planck scale and how to fully reconcile quantum mechanics with general relativity. Modern research continues to push boundaries. Recent discoveries include more detailed observations of black holes, gravitational waves, and the early universe through advanced telescopes and detectors. These provide indirect support and constraints for quantum gravity theories. Practical applications are mostly theoretical, helping physicists refine models of the universe and develop new mathematical tools. Future directions may include new experiments in particle accelerators, space-based gravitational observatories, and advances in computational physics to simulate quantum spacetime. Quantum gravity also offers philosophical insights. It challenges our understanding of reality by suggesting that the universe may be fundamentally different from what we perceive. Space and time might be emergent concepts rather than absolute backgrounds, and matter and energy may interact with a deeper, quantum fabric. This changes our view of the cosmos, making us realize that the universe is more mysterious and interconnected than previously imagined. In conclusion, quantum gravity in cosmology explores the intersection of the tiniest particles and the vast universe. It combines decades of scientific inquiry and modern theoretical innovation to explain phenomena that classical physics cannot. The main points include the attempt to unify quantum mechanics with general relativity, the potential to understand the early universe and black holes, and the ongoing challenges that drive current research. Reflecting on this topic reminds us that science is not just about facts but about curiosity, imagination, and the desire to understand our place in the cosmos. The pursuit of quantum gravity encourages further exploration and inspires a deeper wonder about the universe and its hidden laws. Black hole thermodynamics. Black holes are among the most mysterious objects in the universe. Imagine a place in space where gravity is so strong that nothing, not even light, can escape. These cosmic phenomena have fascinated scientists and thinkers for decades. Black hole thermodynamics is a field that studies these enigmatic objects through the lens of heat, energy, and entropy. Understanding this subject helps us explore the limits of physics and the nature of space and time itself. It matters because it connects two fundamental theories of science, quantum mechanics and general relativity. At its core, black hole thermodynamics is the study of how black holes behave like ordinary thermodynamic systems. Just like a hot cup of tea has temperature and energy, black holes have properties such as temperature, entropy, and energy. The basic principles include the four laws of black hole mechanics, which are similar to the laws of thermodynamics. A key component is the event horizon, the boundary beyond which nothing can return. Another important component is the singularity, the infinitely dense point at the center. Together, these features allow black holes to follow predictable rules despite their extreme nature. The idea of black hole thermodynamics began in the early 20th century. The concept of a black hole itself emerged from Einstein's theory of general relativity. Key contributors include Stephen Hawking, Jacob Bekenstein, and John Wheeler. Bekenstein proposed that black holes should have entropy, suggesting they hold information about everything that falls into them. Hawking later discovered that black holes emit radiation, now called Hawking radiation, implying they have a temperature. Milestones in development include the formulation of the 4 laws of black hole mechanics, which laid the foundation for the connection between gravity, quantum mechanics, and thermodynamics. Black hole thermodynamics works in a fascinating way. First, matter and energy fall into the black hole, increasing its mass. This process changes the area of the event horizon, which is directly related to the black hole's entropy. At the same time, Hawking radiation allows black holes to slowly lose mass, shrinking over time. These interactions follow key equations, such as the relationship between a black hole's surface gravity and its temperature, or the proportionality between its horizon area and entropy. Together, these dynamics show that black holes are not completely isolated but participate in the universe's energy flow. The implications of black hole thermodynamics are profound. Physically, it suggests that information might not be lost forever inside black holes, leading to the famous information paradox. Observational evidence includes detecting radiation emitted from black holes, although this radiation is extremely faint and difficult to observe directly. The study also connects to other areas of physics, including quantum field theory, statistical mechanics, and even cosmology, providing a deeper understanding of the universe's structure and evolution. Despite the progress, many challenges remain. Current limitations include the inability to directly observe the microscopic behavior of black holes. There are debates about how information is preserved and how Hawking radiation exactly works. Some fundamental problems remain unresolved, such as the precise nature of singularities and the reconciliation of quantum mechanics with gravity. These open questions make black hole thermodynamics a vibrant and active area of research, inviting scientists to explore further. Modern research has uncovered new insights. Scientists study black hole thermodynamics using both theoretical models and advanced simulations. Practical applications include understanding high-energy astrophysical phenomena like quasars and the evolution of galaxies. Theoretical applications involve developing quantum gravity theories and testing the limits of general relativity. Future directions include studying smaller black holes that may have formed in the early universe and investigating the role of entropy in cosmological processes. Black hole thermodynamics also offers philosophical insights. It challenges our understanding of reality by suggesting that information, energy, and even time are interconnected in ways we cannot fully observe. It changes our view of the universe, showing that even the most extreme objects obey rules similar to everyday physics. By studying these cosmic mysteries, we gain a deeper appreciation for the order and complexity underlying the cosmos. In conclusion, black hole thermodynamics combines physics, philosophy, and imagination. It shows that black holes are not just empty traps but dynamic systems with temperature, entropy, and energy. From its historical roots to modern research, this field bridges gaps between theories and invites endless curiosity. Understanding black holes encourages us to question the universe, explore its hidden rules, and continue searching for knowledge beyond what is visible. The study of these cosmic giants reminds us that science is not only about answers but also about the wonder of discovery.